What if the prettiest galaxies tricked us into ignoring the biggest ones? And what if the first maps of the sky hid a quiet secret that took centuries to notice? We're about to pull on that thread. In a few minutes, you'll see how a handful of early sketches and one huge argument shaped what we think a galaxy looks like. You'll also find out why the most common giants in the universe don't look like the posters on your wall. Here's the plan for today. We're going back to the start of galaxy hunting. We'll look at how people mapped fuzzy lights with tiny, shaky telescopes. We'll meet the artists who drew them. And we'll see how spirals, the flashy ones with swirls and colour, stole the spotlight, while the quiet, round giants were pushed to the edge of the page. The problem is simple, but sneaky. When you first look at the sky through an old telescope, spirals pop. They have shape. They have drama. They look like storms frozen in space. Elliptical galaxies don't. They look like soft glows, almost like smudges. So for a long time, if you asked, what is a galaxy? Most people pictured a spiral. But that picture isn't the full story. The early maps built a bias into our minds. And that bias still lingers today. Let's start at the beginning, back when galaxy wasn't even the word most people used. In the 1600s and 1700s, small telescopes showed the sky as a handful of bright stars and a lot of mystery. Astronomers kept running into tiny fuzzy spots. They called them nebulae, which just means clouds. Some were real gas clouds. Some were star clusters. And some were other galaxies far beyond our own. But no one knew that yet. Charles Messier, a French observer in the late 1700s, wanted to find comets. Comets were the big deal then. They moved. They changed. They got your name in the news. The problem was that the sky is full of faint, fuzzy things that look like comets if you're tired, cold, and squinting through glass that fogs up. Messier started keeping a list of these fake comets so he wouldn't waste time chasing them. That list became the famous Messier catalogue. If you've heard of M31, M87, M32, or M81, that M is Messier, putting down a line in his notebook 2.5 centuries ago. Messier didn't know which fuzzy things were galaxies. He just knew they weren't comets. But his sketches and brief notes, paired with drawings from other observers, set a pattern. Anything with a swirl, anything with a clear shape, got attention. A spiral drawn with a few curved strokes feels like a find. A round glow with no detail. Easy to skip, easy to log as faint, round, no stars resolved. Move ahead to the 1800s. Telescopes got bigger. The drawings got better. On a cold Irish estate, Lord Rosse pointed a monster of a telescope at the night. His team built a 72-inch reflector from metal, hung from chains. It was a beast, but it could see what smaller scopes missed. In 1845, Rosse looked at the object we now call M51, and he drew the first clear spiral arms. That sketch is famous. It lit up the community. If you were an observer then, spirals became the thing you wanted to catch. They were proof your telescope worked. They were proof your skill was real. This is where spirals started to rule the story. They were rare, but once you saw one, you couldn't unsee it. The lines were bold. The shape was obvious. People started to expect drama. So when someone found another faint glow that didn't show arms, it felt less exciting. The early atlases kept the trend going. Plates and pages that got passed around clubs and universities often featured the showpieces. The showpieces were spirals, and spirals stole the show. But in the middle of all that hype, something else was happening. New tools were coming in. Photographic plates replaced hand drawings. Photography didn't get bored. It didn't blink. It could stare at the sky for hours. Long exposures pulled in light the eye would miss. And when plates went deep, a lot of those boring round glows swelled into view. Suddenly, the sky looked full of fat ovals and soft halos with bright centers. Those were elliptical galaxies, hiding in plain sight. Even with photos, spirals still had the charm. They gave you a pattern to trace. They looked like they were spinning. They made sense to our brains. On the plate, you could point at a spiral and say, "Look, that's the structure." With an elliptical, you saw brightness fading toward the edge. You saw a smooth curve of light, not much else. For many people, that felt like less. Here's a key point. The human eye and brain are drawn to edges, arms, and lines. The early sketches and photo plates fed that bias. The instruments picked up what we were already primed to love. This shaped public taste, student textbooks, and even what objects got time on big telescopes. It didn't mean ellipticals were rare. It meant they were ignored. By the early 1900s, a new question shook the community. Are these nebulae part of our galaxy, or are they island universes far beyond the Milky Way? This turned into the great debate in 1920 between Harlow Shapley and Heber Curtis. One argued that the Milky Way was huge and the nebulae were inside it. The other argued that some nebulae were galaxies of their own. Old sketches and new plates both got pulled into the fight. At the same time, Vesto Slipher measured redshifts for many nebulae. He found huge speeds, far beyond what stars in our galaxy show. That hinted these things were very far away. In the 1920s, Edwin Hubble used Cepheid variable stars to measure distances, and the case closed. Some of these fuzzy spots were galaxies outside the Milky Way. The universe opened up overnight. The catalogues with little drawings and quiet notes turned into maps of a vast city of galaxies. Once galaxies became real, Hubble did something that shaped how we talk about them even today. He arranged them by appearance into a sequence, often called the tuning fork. Ellipticals on one side, then two arms of spirals and barred spirals on the other. It was a neat, clean picture. It made sense on a chalkboard. It made sense in a book. But think about what that did for attention. A tidy fork with arms points your eyes to the arms. The spirals in the pictures had details. The ellipticals were circles and ellipses with labels like E0, E3, E7. They looked like someone had traced a coin and shaded it in. So in the public mind, and in many classrooms, the galaxy becomes a spiral first. If someone says galaxy, most people picture the Milky Way seen from outside, with blue arms and dark dust lanes. It's striking. It's pretty. It's a single photo on a poster. But if you ask, which kind is most common in big clusters? Which kind holds some of the most massive black holes? Which kind rules the centers of the largest galaxy cities? The answer often is ellipticals. Why did ellipticals get forgotten? 3 reasons come up again and again. First, they are smooth. No arms, no obvious dust lanes, no bright blue knots. That makes them hard to sell in a single glance. Second, they are old. Their stars are mostly older and redder, so the color is not as bold on short exposures. Third, surface brightness matters. Many ellipticals have light spread across a big area, so on a small plate or a quick look, they can seem faint even if they are huge. There's also a hardware story. Early telescopes had limits. Mirrors and lenses had issues. Observers had to pick targets. You can only stare at so many things in a night. So people often chased what they could confirm and draw. Spirals were a clear win. See arm, draw arm, done. Ellipticals took patience. You had to measure light carefully, look for subtle twists in the shape, and note the way the brightness fell off. That kind of work grew later, with better tools and more time. There's a social part to this too. Astronomy clubs and magazines loved photos that wow readers. Think about what gets shared today on social media. The same thing happened in earlier times with plates passed hand to hand. Show a spiral with arms and a bright core, and everyone leans in. Show a glowing oval, and people might nod but move on. Over decades, these simple choices add up. The spiral becomes the poster child. The elliptical becomes the background. Yet when you zoom out and look at clusters, a different picture appears. The central galaxy in a rich cluster is often a giant elliptical. It can be many times the size of the Milky Way. Its light spills out in a soft halo that blends into the faint glow of stars drifting between galaxies. These giants are like city centers in the universe. They sit where many paths cross. They've eaten smaller neighbors over billions of years. They've lived long lives and show it in their smooth faces. Some of the first clear photos of those giants came with longer exposures and bigger mirrors in the mid-20th century. Observers started to see faint shells, ripples, and streams in the halos of ellipticals. Those are scars from past mergers. Suddenly, the boring galaxies told stories. The smooth glow wasn't empty. It was a record of many meals. It held clues about how galaxies grow by merging. It held signs of a black hole binding the center. It held the calm light of stars that had burned for a very long time. If you go back to early sketches with this in mind, you see how much was missed. A round glow that was logged as faint, featureless, might, under deep imaging, show long, ghostly arcs. You might see one side of the halo brighter than the other because it's still settling after swallowing a smaller galaxy. None of that would show up in a quick look. It needed time, patience, and a tool that doesn't blink. Let's pause on the artists who built our first ideas. Messier's lists, William Herschel's sweeps, his son John Herschel's southern sky notes, Lord Ross's spiral arms. Later, James Keeler's photographic surveys at Lick Observatory. They were building a language, what to notice, what to name, what to pass on. When they drew spirals again and again, that language shifted our taste. No one meant to hide ellipticals. It just happened because people chase the things that jump out first. Here's a simple test you can try in your head. Think of 5 famous galaxy images you've seen online or in books. How many are spirals? Probably most of them. Now try to name 5 famous ellipticals. You might think of M87 because of the black hole image. You might think of NGC 5128, which is actually a messy mix, but often labelled with an elliptical body. After that, it gets harder. The fame gap isn't about what's common. It's about what we chose to show. Another factor is colour. Spirals have young stars and glowing gas that show up as blue and pink in many images. Ellipticals are heavy on older stars, which glow yellowish-white. On a poster, blue and pink grab the eye. Yellow-white can look plain unless you know what it means. It means age. It means a long, slow story. It means the galaxy has finished most of its star-making and now lives on a steady budget of old starlight. That's not boring. That's a mood. Let's talk about how those early maps changed once photography took over. At the end of the 19th century and into the early 20th, glass plates started to build sky surveys. With long exposures, the number of known nebulae grew. Catalogues expanded. Positions got better. Sizes got measured. The pretty bias didn't vanish, but the sheer count of things forced people to pay attention to the whole mix. Ellipticals filled the lists because they were everywhere once you looked hard enough. Then came distance. When Hubble measured how far some galaxies were, and we saw the scale of space, the role of ellipticals stood out. In clusters like Virgo and Coma, the giants in the center were ellipticals. Their mass ruled the local gravity. Their black holes were monsters. Their halos blended into the intra-cluster light. If spirals are busy neighborhoods full of gas, dust, and young stars, ellipticals are the downtowns that have seen it all. Old money, you might say. Here's a picture that helps many people. Imagine the universe as a huge city. Spirals are the streets and smaller centers spread out across the map. There are lots of them. They have color, motion, and new life. Ellipticals are the major hubs where many streets meet. They're fewer in number, but huge. They're filled with older residents. They run the town's gravity. They don't show off, but they set the tone. So how did spirals steal the spotlight? Part of it is just the human taste for patterns. Part of it is how we teach with pictures. Part of it is who got drawn first in those old notebooks. And part of it is that when you look for stories of motion, your eye grabs a spiral arm automatically. The arm looks like a hint. It makes you think of motion, even if the arm itself is a density wave, not a trail of stars. Ellipticals ask you to slow down and feel the light itself. They hide their past in smooth curves. They reward longer stares. There's another twist. For a long time, people thought ellipticals were too simple. But with better tools, like space telescopes, digital sensors, and careful math, we learned that simple is not the same as easy. The brightness profile of an elliptical holds a lot of information. The exact way light fades with radius tells you about the merger history and the mass inside. The tiny change in shape from round to slightly squashed shows how stars move in 3D. If a central core looks flat, it might have been scoured clean by a pair of black holes merging and slinging out stars. If it's a sharp cusp, the story could be different. These are deep clues hiding in what first looks plain. Think back to that first strong spiral drawing by Lord Rosse. It made people think the universe was full of spirals. It got printed. It got copied. It turned into a goal for builders. Make a telescope big enough to see spirals. That set a culture. If you built a big scope and saw arms, you knew you'd done it. If all you saw was a soft glow, it felt like a letdown, even if that glow was a giant elliptical, 100 times more massive than a small spiral. So from the start, the spiral became the prize. Now, imagine a different start. Imagine if the first famous drawing had been a huge elliptical with a faint shell on one side and a long tidal tail almost too faint to see. Imagine if observers had turned that into the poster. Maybe students would have grown up thinking of galaxies as soft light with hidden scars. Maybe spirals would be the funny ones. It didn't happen that way, but it shows how much our first maps matter. By the mid-20th century, large surveys began to count galaxy types in a serious way. In clusters, ellipticals weren't just present, they dominated the inner regions. The brightest cluster galaxies were almost always ellipticals. Some were so big, they had to be labelled as a separate class, CD galaxies, with extended outer envelopes that melted into the background light of the cluster. These were the true titans, and they didn't have arms or bright blue patches. They had mass, old stars, and deep wells of hot gas around them. If you look at M87 in Virgo, You can feel that. It looks like a soft sphere of light with a bright center. But inside sits one of the most massive black holes known in the nearby universe. A thin jet of matter shoots out from the core. The halo spreads wide. When the first image of a black hole's shadow was shared, it was that one. Not a spiral's, an elliptical's. That moment quietly told the world that the big stories don't always wear showy arms. Let's pull back to the theme of this episode. Early mapping, first sketches, and how spirals grabbed attention. The simple truth is that the sky is a crowded place. When gear is weak, you lean on simple wins. Spirals gave simple wins. Ellipticals asked for patience that most tools couldn't provide back then. We can forgive those early choices, but we don't have to let them keep shaping our taste today. There's a lesson here that goes beyond astronomy. First impressions stick. Early visuals shape what we think is normal. When better tools arrive, we need to ask if our old taste still serves us. With galaxies, the answer is clear. The quiet giants were always there. We just trained ourselves to look away. So the next time you think of a galaxy, add a second picture in your mind. Keep the spiral. It's beautiful, but also hold the glow of an elliptical. Think about the weight in that light. Think about the age in those stars. Think about the calm after billions of years of motion. Think about a giant sitting at the center of a cluster, steady as a mountain, letting the universe move around it. Here's the key moment I want you to remember. A single drawing in the 1840s lit a fire for spirals that burned for a century. But a single photo in 2019, the shadow of a black hole in an elliptical, quietly moved the center of the stage. It told us that the biggest stories can live in the smoothest shapes. And if we listen closely, those shapes talk. As we move forward in this series, we'll go deeper into the lives of these quiet giants. We'll see how they formed from crashes and mergers. We'll look at the black holes at their cores. We'll visit the clusters they rule. We'll also talk about why, even now, they don't fill posters the way spirals do, and why that's okay. Not all truth is a headline. Some truth is a steady glow that never blinks. To close today, let's bring it back to that first question. Did the prettiest galaxies trick us into ignoring the biggest ones? Maybe they did, for a while. But the sky is patient. The light of those giants has been crossing space for hundreds of millions of years. It reaches us, whether or not we're ready to see it. Now that we are, the map of the universe looks different. It looks fuller, it looks older, and it looks more honest. In the next chapter, we'll slow down inside a single elliptical and learn to read its light the way you'd read rings in a tree. But for now, let this idea sit with you. Sometimes, the most important things don't shout. They shine. A soft hush drapes across the cosmic expanse as we drift deeper into the realm of galaxies. Before us, a great subtle shape emerges in the darkness. A galaxy without the familiar whirl of spiraling arms. Instead of tightly wound ribbons of stars, we see a gentle, ovate glow, like a pale lantern suspended in space. This is an elliptical galaxy, a silent aggregation of countless stars, all held together in a smooth, elongated sphere of light, calm and unassuming. In the stillness of this galactic form, there are no grand designs etched in starry coils. The galaxy's face is unbroken by the arching sweep of spiral arms or the dark ribbons of dense dust. It appears featureless at first glance, a softly gleaming ellipse that might almost be mistaken for a distant star, if not for its size. But as our gaze lingers, we discern the difference. The faint, extended halo of starlight that gradually brightens toward a concentrated center. It is a glow so uniform and diffuse that it hides any single point of brilliance, blending millions of stars into one gentle radiance. For these galaxies, shape is their name, elliptical. Some appear almost perfectly round, gentle spheres of stars, while others stretch into more elongated ovals, as if drawn out by cosmic hands. Yet all share that softly fading edge. No outer rim defines them sharply. Instead, their starlight gradually diminishes into the dark, a slow ebbing of stars as one moves outward. In this way, an elliptical galaxy seems to dissolve at its fringes, its outermost stars drifting lonely, half lost to the emptiness of intergalactic space. These stars are ancient and steady, and they fill the galaxy in every direction like a swarm of fireflies frozen in a cosmic dance. Unlike the youthful suns in a spiral galaxy's arms, hot, blue, and blazing, these stars shine with a mature, golden light. Theirs is a patient luminescence, as if each star has been glowing for eons. In this quiet multitude, stellar lives have come and gone over billions of years, their remnants adding to the galaxy's mass and story. New stars are few here. The clouds of gas that once gave birth to brilliant young suns have long been dispersed or exhausted. All that remains is the collective glow of venerable stars, shimmering together in peace. Without new stars to stir up their surroundings, elliptical galaxies remain tranquil, almost inert, when compared to their more rambunctious spiral cousins. There are no massive stellar nurseries lighting up nebulae in pink and blue, no spiral density waves triggering fresh generations of stars. Instead, the galaxy's energy is subdued. If we could float within this oval realm, we might find it surprisingly uneventful, just a pervasive golden light in all directions, and an ocean of stars moving gently under the pull of gravity. This lack of obvious structure belies the galaxy's enormity. From afar, we see only an elliptical haze, but that soft light is the combined glow of perhaps hundreds of billions of stars. Spread throughout, those stars orbit the galaxy's center in random, intricate paths. There is no single direction to their motion. Unlike the regimented rotation of a spiral's disk, here each star traces its own ancient route, crisscrossing in a gravitational ballet that, over time, smooths out any sharp features. The result is an almost featureless, rounded silhouette, a cosmic sphere that rotates only slowly, if at all, and seems to simply hover in space like a relic of a quieter time. In this universe without whirl, we find a different kind of beauty. It is subtle and stately, the beauty of a well-aged wine versus the bright sparkle of fresh fruit. The galaxy's light neither flickers nor flares, but remains steady, a testament to its stars that have settled into long, stable lives. One can imagine eons passing in this elliptical haven with little change, just the slow burning of stars and the gradual journeys of star clusters wandering through the galaxy's core and outskirts. It is a realm where time stretches languorously and cosmic events unfold on leisurely scales. And although the elliptical galaxy lacks the dramatic spiral arms or glowing nebula highlights, it whispers its story through this very calm. It tells of a universe that does not always need motion to impress. Sometimes, simply existing in a state of gentle equilibrium is its own quiet wonder. The smooth, featureless glow suggests a chapter in cosmic history where chaos has mellowed into order, where tumultuous birth has given way to graceful maturity. In contrast to the majestic pinwheels that captivate our imagination, these oval galaxies might seem understated, but they hold their own form of majesty. They are the silent giants of the cosmos, massive and bright, yet often overlooked. There is humility in their appearance, and yet when we truly look, we recognize how grand a thing it is to gather so many ancient stars into one island of light. Unassuming as they are, they quietly carry the weight of cosmic history, offering their wonders only to those who seek them. Elliptical galaxies also span a tremendous range in size. The tiniest dwarf ellipticals may contain only a few million stars, scarcely more than a large globular cluster. The largest ellipticals, by contrast, hold trillions of stars and can extend over 1 million light-years. Yet across this spectrum, from modest to immense, they all share that family resemblance: a smooth, ellipsoidal glow and a population of ancient stars. At this point in our journey, having known the splendor of spirals, we are invited to appreciate the quiet grace of these ellipticals. They teach us that not all galaxies twirl in a dance. Some stand in serene poise. Their lack of a whirl does not mean a lack of wonder. It is a different kind of cosmic artistry, one etched not in swirling arms, but in a harmonious, diffuse glow. The elliptical galaxy before us floats patiently in the dark, a testament to time and stillness, inviting us to ponder the silent story it carries in its countless old stars. That pale, ghostly glow we see streaming from an elliptical galaxy is more than just a pretty haze. It is a direct clue to the galaxy's age and character. Notice the color of the light, not the bright blue-white of newborn stars, but a gentler shade of yellow-white, like the last light of afternoon, or the glow of a fading ember. In the silence of space, an elliptical galaxy shines in this subdued tone, a sign that its stars are mostly old. It's as if the galaxy carries a candle that has burned low, giving off a warm, soft radiance instead of a fierce blaze. In younger galaxies, brimming with new stars, the illumination has a brilliant, bluish cast. Hot, massive stars, just a few million years old, pour out intense blue and white light, and neon clouds of gas fluoresce under their energy. But such stars live brief lives and die out quickly. In ellipticals, they are long gone. What remains are stars that have settled into peaceful middle and old age. Golden suns, orange suns, and myriad red dwarfs. These stars, cooler and smaller on average, glow with a milder light. As their combined glow travels across the cosmos, by the time it reaches our eyes or our telescopes, we perceive it as that hallmark yellowish-white hue, the signature of an ancient stellar population. There is something ethereal about this light. Through a telescope on a dark night, an elliptical galaxy may appear almost ghost-like, a dim, elliptical smudge against the blackness, with no sharp edges or striking colours. Unlike a nearby spiral whose bright young star clusters and nebulae jump out vividly, the elliptical's light is diffuse and even, requiring patience to appreciate. Astronomers often take long exposures to capture these galaxies on camera, revealing a faint extended glow that might otherwise escape notice. In those deep images, the outskirts of the galaxy seem to vanish into the background of space, as if the galaxy is only half there, a spectral remnant of something that once shone more brightly. But it is not emptiness we are seeing. It is the gentle combined light of billions of aging stars. Many of these stars were born at nearly the same time, long ago when the universe itself was young. Over the eons, they have exhausted the fuel of youth and cooled into steadier, redder stars. Some have swollen into red giants, huge and luminous, but cooler, casting a reddish gold light. Others have become small, dense white dwarfs, the lingering embers of larger stars. These white dwarfs are faint, mere cosmic coals slowly cooling in the dark. Together with countless still glowing stars, they create the galaxy's soft tapestry of light. One could say an elliptical galaxy is illuminated by the ghosts of its past, old starlight from suns that are either in their twilight or long since extinguished. This ancient starlight tells a story. When scientists study the color of an elliptical galaxy's glow, they can infer its history. The dominance of yellow and red tones reveals that most of the galaxy's stars formed billions of years ago. It speaks of a time in the distant past when this galaxy blazed with youthful energy, forming stars in great numbers. That era has ended. The fireworks are long over. Now, in the absence of youthful blue stars, the residual population shines steadily on. Their light is relatively dimmer and softer, not because each star isn't shining bright in its own right, but because the galaxy lacks those few extremely bright beacons that would outshine the rest. Instead of a 1,000-watt spotlight, the elliptical galaxy offers the ambient glow of many steady lamps. In a very real sense, these galaxies are cosmic retirement homes, filled with veteran stars. Wandering through an elliptical galaxy would be like strolling through an ancient city at dusk, lit not by the glare of modern neon lights, but by old lanterns lining quiet streets. The overall illumination is lower, but it has a comforting consistency. The inhabitants, those stars, burn on in quiet contentment, having survived the tumult of youth. They no longer send out the searing ultraviolet flares of the young. They shine with a dignified restraint. Compared to their younger counterparts, these elder galaxies almost seem to hide in plain sight. A lively spiral galaxy announces itself across space with bright patches of starbirth and swirling arms reflecting intense light. An elliptical, by contrast, can blend into the darkness if you're not looking carefully, its light having a quality of a whisper rather than a shout. This is why, despite being common, elliptical galaxies were historically harder to notice. Many of them simply weren't as eye-catching to early observers scanning the skies. They were there all along, huge and significant, but their ghostly pallor made them easy to pass over in favor of flashier galactic spectacles. Yet the ghostly light holds profound beauty. Think of it. The photons reaching us from a large elliptical galaxy might have been traveling for tens or hundreds of millions of years. They left their stars at a time when perhaps life on Earth was just beginning its first delicate experiments, or even before Earth itself had fully formed. By the time those ancient photons arrive and trigger a detector or a human eye, they carry with them the memory of a bygone epoch. In gazing at an elliptical galaxy, we are gazing into the deep past, seeing a stellar community that has been in quiet existence for ages. This pale glow is also a promise of what our own galaxy's distant future might hold. Trillions of years from now, long after the Milky Way has merged with its neighbors and star formation has ceased, an observer from afar may see a faint, reddish orb where our spiral once shone, our Milky Way's eventual ghost. The ellipticals we observe today give us a preview of that fate. Galaxies in their sunset years, still luminous, but gentler, calmer, and quieter than the youthful galaxies we often celebrate. So the ghostly light of the old is not to be mourned, but admired. It is the soft afterglow of creation's blaze, the mature radiance that follows an era of brilliance. In its diffuse gleam, there is the suggestion of wisdom and endurance. These galaxies have seen the rise and fall of countless suns. They quietly illuminate the cosmos with the sum of all that past glory, now settled into a tranquil present. And in that calm, pale light, one can find a deep sense of cosmic history written in a language of colour and faint glow, a story of stars that lived, shone, and faded, leaving behind an eternal gentle light. In the early days of extragalactic astronomy, the heavens presented a gallery of shapes without obvious rhyme or reason. Through their telescopes, astronomers saw pinwheels with spiral arms, amorphous clouds of stars, and smooth oval glows, like the ellipticals we have come to know. It was a cosmic zoo of forms. As our understanding grew that these were entire galaxies, island universes far beyond the Milky Way, the need to classify them became clear. For a time, even that fundamental point was debated. In 1920, astronomers argued fiercely over whether the so-called spiral nebulae were part of our own galaxy, or separate galaxies in their own right. Edwin Hubble ended that debate a few years later by measuring the great distance to the Andromeda Nebula, proving it lay far outside the Milky Way. With the existence of countless island universes confirmed at last, the challenge became how to bring some order to their bewildering diversity. The answer began to emerge in the late 1920s, when a visionary astronomer named Edwin Hubble stepped forward to impose a kind of cosmic order. Hubble, working at the Mount Wilson Observatory with its cutting-edge telescope, spent nights poring over photographic plates of galaxies. On those glass plates, he observed that some galaxies had the grand design spirals we've described. Others appeared as featureless ellipses, and still others fell somewhere in between. In 1926, he published a system to categorize galaxies by their shape, a scheme that would become famous as Hubble's tuning fork diagram. With this, Hubble essentially drew a family tree for galaxies, laying out the major types in a logical sequence. At one end of the diagram were the elliptical galaxies, and at the other end, the spirals split into two branches. To visualize Hubble's tuning fork, imagine a two-pronged fork with a handle. The handle represents the ellipticals. Hubble labeled them with the letter E, followed by a number from 0 to 7, indicating how stretched out they appeared. A galaxy classified E0 looks nearly round, while an E7 is quite elongated, like a cosmic egg. All along that handle, the ellipticals sat in order of shape, each an oasis of smooth starlight without any trace of arms. Then the fork split into two prongs. Down one prong were the ordinary spirals, with tightly wound SA-type spirals near the split and increasingly open-armed SC spirals further along. Down the other prong were the barred spirals, galaxies with a bar of stars through their centre, labelled SBA, SBB, and SBC, likewise ranging from tightly wound to more spread out. In the middle, connecting to the handle, lay a transitional type. The lenticular galaxies, labelled S0, which have a disc shape like spirals, but no visible arms, perhaps a midway point in appearance between an elliptical and a true spiral. In Hubble's original thinking, these categories carried an implicit temporal suggestion. He called ellipticals early type galaxies and spirals late type. It was tempting to imagine that an elliptical galaxy might one day unfold into a spiral given enough time, or that spirals were ellipticals that had developed arms. The tuning fork diagram, after all, led from the smooth handle to the branching arms. But even Hubble cautioned that this was not necessarily an evolutionary path, merely a classification by appearance. And indeed, later discoveries showed that galaxies evolve in more complex ways. Spirals can collide and merge into ellipticals, for example, rather than the other way around. Still, the terminology of early type and late type remained, echoing that initial intuition of a sequence from simpler to more structured forms. For the first time, astronomers had a clean framework to talk about galaxies. The previously overlooked ellipticals now had a proud place in this cosmic order. No longer just faint nebulae, they were recognized as a fundamental category of galaxy, co-equal with the magnificent spirals. Hubble's scheme gave astronomers a common language. They could say E5 to describe a moderately elongated elliptical, or SB for a spiral with medium-tight arms, and colleagues around the world would understand exactly the kind of galaxy being referenced. This classification was more than just cataloguing. It shaped how we think about galaxy life stories. Ellipticals, by virtue of their place on the diagram, were perceived as old and perhaps primordial, whereas spirals, with their intricate structures, seemed more youthful or developed. We now know ellipticals often form through ancient mergers and interactions, but in Hubble's time, their origin was a mystery. What mattered then was that a sense of order had been brought to chaos. The universe's diversity of island universes could be neatly sorted into a few basic types, like sorting seashells by shape after a cosmic tide. Imagine the relief and excitement of that era. Each galaxy image that swam into view on a photographic plate could now be identified. This one a spiral, that one an elliptical. It was as if the cosmos had been teaching us its own taxonomy. Elliptical galaxies, with their smooth glow, were no longer an odd curiosity. They were the starting point of Hubble's grand diagram, the foundation of the galactic family. In the grand design that Hubble sketched, every galaxy found its place, and the silent giants of the cosmos were enshrined as the opening chapter in the story of galactic forms. Hubble's tuning fork has endured as a classic concept. To this day, in textbooks and museums, you will find diagrams illustrating galaxy types, a tribute to that early effort to make sense of the universe. It reminds us that behind every elegant ordering of knowledge is someone's careful observation and intuition. Under the faint glow of distant galaxies, Edwin Hubble discerned a pattern. He saw that the calm ellipticals and the dynamic spirals were threads in a single tapestry. In naming and arranging them, he helped reveal a hidden harmony in the heavens, a cosmic order that had been there all along, waiting for a mind to perceive it. So, in the panorama of galaxies, we now had a map. Ellipticals stood as one prominent realm on that map, understood and appreciated in a new light. They were no longer merely the other galaxies lacking spiral arms, but one of the primary archetypes in the universe's grand design. This was the birth of order in galactic astronomy, a framework that would guide generations of astronomers as they delved further into how galaxies form, grow, and interact. And at the heart of that framework, quietly shining, were the ellipticals, the elegant elder statesmen at the beginning of Hubble's cosmic tuning fork. Indeed, far from being lonely wanderers, most galaxies live in communities. These communities can be as small as groups of a few galaxies, or as vast as clusters containing hundreds or even thousands. A galaxy cluster is like a great city of the cosmos, a dense hub where galaxies crowd together, bound by their mutual gravity. And towering above the galactic skyline of such a cluster, you will often find a giant elliptical galaxy, the brightest and most massive resident of this cosmic city. For every such giant that reigns, there are dozens or even hundreds of lesser galaxies sprinkled throughout the cluster. Many of these are small elliptical galaxies themselves, dwarfs that contain only a fraction of the stars of a large galaxy. Individually, they are faint and easily overlooked, but in aggregate, they swarm like a flock of sparrows around the cluster's towering eagle. These diminutive galaxies drift through the cluster's expanse, adding to the rich population that gravity has gathered in one place. In the heart of a galaxy cluster, the giant elliptical reigns supreme. It often sits close to the cluster's center of mass, anchoring the swarm of smaller galaxies that buzz around it. Imagine a swarm of glittering fireflies around a steady lantern. The comparison hints at the scale. These central ellipticals are truly titanic. They can span an immense distance, hundreds of thousands of light years across, sometimes approaching 1,000,000. Containing trillions of stars, they outshine all their neighbours. In fact, the central elliptical in a rich cluster is usually the single most luminous galaxy in that cluster, often by a wide margin. It's as if all the streetlights of a town were gathered into one enormous beacon at the town square. These giant ellipticals, sometimes called central dominant galaxies, have grown to their impressive size over eons, and the cluster environment has been their nurturing ground. In the crowded downtown of a cluster, galaxies frequently drift near each other. Smaller galaxies that venture too close to the central giant may not escape its gravitational grip. Some are slowly stripped of their stars. Others might be entirely devoured in a cosmic act of cannibalism. With each such encounter, the giant elliptical adds to its vast collection of stars, growing ever larger and more luminous. One can almost imagine it as an ancient emperor gathering the spoils of war, becoming more powerful with each conquest. Look closely at a massive galaxy cluster, and you may notice a gentle glow permeating the space between the galaxies. This is the intracluster light, made up of stray stars that have been thrown free from their original homes during gravitational skirmishes. These orphaned stars now drift through the cluster, no longer bound to any single galaxy. The central giant elliptical often bathes in this ghostly backdrop of lost starlight, its own outer edges blending into the hazy illumination. In the giant galaxy's halo, faint shell-like ripples may also be visible, ghostly scars from galaxies it has consumed, slowly fading over time. The sheer mass of a central elliptical is hard to fathom. Imagine a galaxy 10 times the mass of the Milky Way, or even more. The core alone might contain as many stars as a whole normal galaxy. At its centre lies a deep gravitational well, often harbouring a supermassive black hole that dwarfs even the ones found in typical galaxies. Occasionally, if gas finds its way into this black hole, enormous jets of energy can be unleashed, shooting out of the galaxy's core and heating the surrounding cluster gas. The galaxy known as M87 in the Virgo cluster, for example, shoots a jet of particles from its centre, a sign of the powerful black hole deep inside. M87's jet extends far into space, a brilliant beam of energy piercing through the galaxy's halo. It is a striking exception in an otherwise tranquil-looking giant. But despite such dramatic capabilities, to the eye, the central elliptical remains a picture of calm, a vast, softly radiant sphere presiding over the clustered multitude. Each galaxy cluster has its own central drama. In the Virgo cluster, relatively close to us, one giant elliptical, Messier 87, dominates the centre, quietly influencing the orbits of smaller galaxies around it. In the more distant Coma cluster, two gargantuan ellipticals share the throne, enveloped by an entourage of thousands of galaxies. These central titans define the character of their clusters. They are not only landmarks in the cluster landscape, but also key players in the cluster's evolution. Their strong gravity helps bind the cluster together, and their interactions with other galaxies can drive phenomena like shockwaves in the hot gas, or the creation of new streams of stars torn from passing companions. Despite their overwhelming size and influence, giant ellipticals keep a low profile in terms of appearance. From afar, they look like any other elliptical galaxy, just larger and more luminous. There are no flashy spiral arms to draw attention, no dramatic bursts of colour, just an extended realm of starlight that gradually tapers into darkness. It's as if nature has concentrated a whole collection of galaxies into one enormous, glowing ball and set it gently at the cluster's center for all to revolve around. The spectacle is subtle, a diffuse glow in the cluster's core that on a telescope image appears as a soft haze. Yet that haze is the light of trillions of stars, unified in one entity. Consider for a moment the idea of standing at the outskirts of such a giant elliptical, looking outward. All around, the sky would be filled with the lights of other galaxies in the cluster, scattered like distant city lights on a dark night. The gravity holding you and everything around you is dominated by the mass of the colossus behind you. In the far distance, its companion galaxies wheel around, bound in a slow dance by the cluster's gravity. The central giant itself changes little over time. It has long ago used up or lost the gas needed to spark new stars. It simply keeps shining with the combined output of all its aged stars, a steady beacon at the hub of cosmic activity. Giant ellipticals of clusters are, in many ways, the ultimate titans among galaxies. They are a culmination of countless smaller galaxies' lives and deaths, the end result of a long history of merging and melding. In their quiet brilliance, they hold the stories of many collisions and assimilations. Every faint glow at their outskirts, every globular cluster in their halo, each may once have belonged to another galaxy that has since been absorbed. Now all that history is pooled together, orbiting a common center and shining as one. These cosmic giants remind us that even in the busiest venues of the universe, the bustling galaxy clusters, there can exist a kind of order and hierarchy. Amid the apparent chaos of hundreds of galaxies mingling, one finds a central calm, embodied by the giant elliptical that sits like a monarch in court. Its dominion is vast, its presence quietly respected by the surrounding throng. Through the grand scale of these clusters, we witness nature's inclination to form structures within structures, stars into galaxies, galaxies into clusters, and at each level, a few giants leading the way. The giant ellipticals stand as beacons in the cosmic cityscape, silent powerhouses that give structure and focus to the otherwise overwhelming sprawl of the clusters they inhabit. To find one of the grandest elliptical galaxies, we journey to the Coma Cluster, a vast congregation of over 1,000 galaxies, roughly 300 million light-years away. In the heart of this cluster lies NGC 4889, a behemoth among behemoths, serenely presiding over the cosmic city around it. From Earth, NGC 4889 is too distant to see without a powerful telescope, but long exposures reveal it as a soft glow amidst the crowded background of the cluster. The light we capture from NGC 4889 began its voyage when life on our planet was in its distant past, long before humans, even before the age of dinosaurs. We are, in effect, peering into a deep historical tableau, witnessing this galaxy not as it is now, but as it was 300 million years ago. NGC 4889 appears as an extended haze of starlight, slightly elongated and without distinct features. It outshines every other galaxy in the Coma Cluster, anchoring the cluster's core with its tremendous mass. Surrounding it are countless smaller galaxies, like a cosmic court gathered around their sovereign. One of its near neighbors, almost as large, shares the central stage, another giant called NGC 4874. But NGC 4889 holds the title of brightest. Its halo of stars extends far into space, gradually blending with the general glow of the cluster itself. If you could hover just outside this galaxy, you would see a vista filled with galaxies in every direction. The Coma cluster's many members, but NGC 4889 would dominate the foreground as an immense, diffuse ball of light. What truly sets NGC 4889 apart is the invisible titan lurking at its core, a supermassive black hole of almost unfathomable size. Astronomers estimate this black hole's mass at roughly 20 billion times that of our Sun, one of the most colossal ever measured. By comparison, the black hole at the center of our Milky Way is thought to be about 4 million solar masses. NGC 4889's dark heart is so vast that it could hold our entire solar system many times over. Yet despite its mind-boggling presence, this black hole now lies quiet. The galaxy around it has little gas left to feed the beast, and so the black hole slumbers in a dormant state. It was not always so tranquil. In the distant past, when NGC 4889 was younger and rich with gas, its black hole likely feasted ravenously. As matter spiraled into that gravitational pit, it would have ignited with tremendous energy, possibly making NGC 4889 a quasar, one of those brilliant beacons of the young universe that can outshine whole galaxies. Those times have long passed. Today, NGC 4889 wears a veil of quiet dignity. The stars we see now tell of an old, evolved galaxy that has consumed its fuel and settled into graceful maturity. The legacy of its violent youth is written in the enormous mass of its black hole and the sheer scale of the galaxy itself. Standing inside NGC 4889, if one could do so, would be an awe-inspiring experience of scale and history. The galaxy's core would be densely packed with old stars, bathing the surroundings in a gentle, perpetual twilight. Farther out, the star density would gradually drop off, until beyond the galaxy's boundaries, the intergalactic night of the Coma cluster would begin, dotted by the lights of neighboring galaxies. In the core, night would never truly fall. So many stars would crowd the sky that a perpetual starlight would glow in every direction. The pull of gravity from NGC 4889 binds a vast region, helping keep the Coma cluster's galactic community together. Yet even this giant cannot single-handedly bind the cluster. Observations suggest an invisible presence, dark matter, providing additional gravity to hold the cluster together, a mysterious scaffold upon which all these galaxies hang. And though you might not see the central black hole, you would feel its presence indirectly in the motions of stars near the core. One might observe the innermost stars whipping around at remarkable speeds, compelled by the powerful gravity of that unseen mass. NGC 4889, discovered by astronomer William Herschel as a faint smudge in 1785, has proven to be a cosmic colossus. It reminds us that the universe often hides its most extreme marvels behind deceptively simple facades. To the eye, it's just a pale, elongated blur. But within that blur lies the mass of trillions of suns and the darkest of hearts that nature can conceive. As we drift away from the Coma cluster, leaving NGC 4889 to its silent vigil, we carry with us a profound sense of the immense scales and deep time that such a galaxy represents. From the distant Coma cluster, we move to a much closer gathering of galaxies. The Virgo cluster, about 55 million light-years away, in the direction of the constellation Virgo. Here we encounter another giant elliptical that, while nearer to us, is no less remarkable. This is Messier 87, often simply called M87, a colossal galaxy that dominates the Virgo cluster, much as NGC 4889 does its own domain. In the dark skies of Earth's northern hemisphere, M87's location can be pinpointed with a telescope, though to the eye it appears only as a dim, round blur. When Charles Messier first catalogued it in 1781, he noted a nebulous patch of light, never suspecting that he had found an entire galaxy of stars. Now we know M87 to be one of the most massive galaxies in our cosmic neighborhood. M87 sits at the center of the Virgo cluster, like a hub in a wheel. Around it, some 2,000 galaxies, large and small, are scattered throughout the cluster, bound together by gravity. M87 itself contains several trillion stars, far more than our Milky Way. If you were to compare, our galaxy's visible stars number only a few 100 billion. M87's girth and mass are extraordinary. Its luminous halo of old stars spreads out roughly 500,000 light-years, gradually tapering into intergalactic space. Scattered within that halo are an astonishing number of globular clusters. Around 15,000 of these ancient star clusters swarm around M87, like bees encircling a giant hive. The Milky Way, by contrast, has only about 150 globular clusters. Each of those globular clusters is itself a microcosm of hundreds of thousands of stars, all orbiting the great elliptical in obedient tribute. For context, the Virgo cluster is the central hub of the larger Virgo supercluster of galaxies, of which our own Milky Way is an outlying member. In a sense, M87 sits near the gravitational center of the vast collection of galaxy groups and clusters that includes our home. A reminder that even our galactic neighborhood is subtly influenced by these giants. For eons, galaxies like the Milky Way have been gravitating subtly toward the Virgo cluster, drawn by its immense mass. Though this motion is imperceptible on human timescales, it underscores the far-reaching influence of M87 and its cluster. Like NGC 4889, M87 harbors a supermassive black hole at its core, a black hole that has become famous in human history. In 2019, telescopes across the Earth synchronized to produce a picture of this object, marking the first time we directly beheld a black hole's shadow. The image showed a dark central silhouette surrounded by a ring of golden light, the hot, glowing gas just outside the black hole's event horizon. This black hole, often referred to as M87 star, weighs on the order of 6.5 billion suns. While smaller than NGC 4889's Leviathan, it is still among the most massive known and far more immense than the one in our Milky Way. M87's black hole is not entirely quiet either. It powers a relativistic jet, a narrow beam of particles and energy that blasts out from the galaxy's core. Even in visible light images, this jet can be seen as a faint bluish streak extending tens of thousands of light-years from the center. It is a striking signal that deep inside this peaceful-looking galaxy, incredible energies are at play. Despite these energetic phenomena, M87's overall demeanor is calm and stately. Through an amateur telescope, one doesn't see the jet or the fireworks in the core. One sees only a diffuse, softly glowing orb with a brighter center. All the drama is hidden in that core, and in wavelengths of light our eyes cannot detect. Visually, M87 appears as a ghostly glow, much like other ellipticals, only significantly larger and brighter when viewed through powerful instruments. The galaxy's light has that same yellow-white cast, evidence of its predominantly old stellar population. In photographs, M87 doesn't command attention the way a sculpted spiral galaxy might. Instead, it exudes a subtle, steady presence. For those familiar with the night sky, it's humbling to realize that this unassuming glow in Virgo is the powerhouse of an entire cluster. M87's gravity influences the motions of galaxies thousands of light years away within the Virgo cluster. It has likely grown large by cannibalizing neighbors over billions of years. It stands now as an elliptical giant that has outlasted the fireworks of its youth. If we were to observe the Virgo cluster from afar, M87 would be the beacon marking its center, a great lamp shining in a region of the universe relatively near our own local group of galaxies. As we contemplate M87, we are reminded again of the hidden wonders these ellipticals hold. One gave us our first direct glimpse of a black hole, opening a new window on the universe's deepest mysteries. Yet these galaxies also whisper of longevity and endurance. M87 has existed for billions upon billions of years, its stars aging gracefully as the galaxy slowly evolves. It will continue to shine long after younger, more flamboyant galaxies have burnt out or transformed through collisions. In its collected light, we see the accumulated glow of ancient suns, a cosmic memory of epochs long gone, still illuminating the darkness. Our journey to M87 and back has been a voyage through both space and time. From the near reaches of the Virgo cluster to the far expanse of Coma, we have met two silent titans and glimpsed their secrets. These galaxies, one relatively near, one far, exemplify the quiet might of ellipticals. They anchor the enormous cosmic structures of clusters and harbour the mysteries of black holes at their cores, all while glowing with the diffuse, gentle light of uncountable aged stars. They are beacons of a universe that has grown old and settled, even as it continues to expand outward. They often slip from popular view, quietly existing as forgotten giants until we seek them out. Now that we have glimpsed their grandeur, our curiosity only grows. These silent titans still hold untold stories, and as our cosmic journey continues, we find ourselves eager to uncover what further secrets they may reveal. Much remains to be discovered about these galaxies, how they formed, how they influence their surroundings, and what their ultimate fate will be. In truth, our exploration of the elliptical titans has only just begun. Drifting in the silent deep of space, a giant elliptical galaxy glows with gentle, diffuse light. Unlike the whirling spirals, with their arms of young stars and gas, this galaxy is an ethereal, ellipsoidal cloud, unassuming, calm, and seemingly motionless. To an observer's eye, it appears as a peaceful beacon of ancient starlight, a cosmic island that has long since settled into stillness. Yet, that tranquil exterior is deceptive. Beneath the quiet facade lies the memory of a dramatic and violent origin, a story written in cosmic fire and collision. They might appear as peaceful beacons of ancient starlight now, but behind their tranquil facade lies a dramatic origin story, one forged in cosmic fire and collision. In the infancy of the universe, galaxies often met and merged, sparking brilliant bursts of star formation amid the wreckage. It was a time of celestial upheaval, when gravity drew young galaxies together in a chaotic dance, and in that dance, the seeds of the first elliptical titans were sown. In those early epochs, the universe was smaller and more crowded than today. Galaxies were closer together, still gathering mass along tendrils of the cosmic web. Inevitably, many of these youthful galaxies found themselves on collision courses. What began as separate islands of stars would drift into one another's gravitational embrace. As they converged, their shapes distorted into long tidal tails of stars, and their contents mingled. Every such encounter was a transformative event, altering the galaxies involved and paving the way for something new. Picture, if you can, two galaxies on such a collision course. They draw closer and closer, each a majestic swirl of billions of stars. As they near impact, their delicate spiral arms are yanked outward by tidal forces, stretching like taffy into luminous streams. The first direct encounter sends ripples through both galaxies, casting stars and gas adrift. The collision unfolds gradually, a slow-motion catastrophe lasting tens of millions of years. To cosmic spectators, it would be a scene of both destruction and creation, chaos and beauty intertwined. Remarkably, amid all this havoc, individual stars almost never collide directly with one another. The gulfs between them are simply too immense. The violence is instead gravitational and gaseous. Stars are flung into new trajectories, and great clouds of interstellar gas crash together. Those gas collisions trigger brilliant fireworks, compressing material to ignite new stars by the thousands. The galaxies begin to intermingle in a turbulent embrace, unleashing both destruction and creation in equal measure. It is an epic cosmic event that transpires over hundreds of millions of years, utterly reshaping the galaxies involved. After the carnage, the two galaxies gradually coalesce into one. In the aftermath, the merging galaxies undergo a period of chaotic adjustment. Stars that were flung out are now bound in new orbits around a common center. The combined system wobbles and rings with the reverberations of the encounter. Bit by bit, over additional eons, it stabilizes into a roughly spherical mass of stars. The debris of the collision, streams and plumes of stars, either fall back into the remnant or continue drifting as tenuous extensions of the new galaxy's halo. Eventually, a kind of calm is restored, but it is the calm after a storm, with the landscape forever changed. Over millions of years, their stars mix together, losing all trace of the graceful spiral patterns they once held. What remains is a single swollen galaxy, shapeless and diffuse compared to its progenitors. This newborn elliptical galaxy is a cosmic phoenix rising from fire, an oval island of stars left drifting where two disks once spun. The violence of the collision has erased the old forms and created a new giant, one that shines with the combined light of trillions of stars. Even now, long after the chaos has settled, some elliptical galaxies carry whispers of their violent youth. Astronomers sometimes find faint loops and shells of stars encircling an elliptical galaxy, like ripples frozen in time. These ghostly rings are the remnants of galaxies torn apart and absorbed. They are subtle scars, barely visible, but they tell a tale of past collisions, each shell a memory of a smaller galaxy that once ventured too close and was swallowed. In this way, an elliptical reveals its history, layer upon layer of stars, each layer a chapter from an ancient cosmic saga of collision and merging. For example, astronomers have marveled at images of an elliptical galaxy named NGC 474, which shows multiple concentric shells faintly encircling it. It's as if the galaxy's past meals left visible ripple marks, like a pebble dropped in a pond. Each shell in NGC 474 likely marks the remains of a smaller galaxy it absorbed long ago, now stretched out into a languid loop of stars. Such striking features offer direct visual evidence of the cannibalistic events that build up ellipticals over time. Indeed, Elliptical galaxies often dominate the densest regions of the cosmos. In rich galaxy clusters, where dozens or hundreds of galaxies are crowded together, collisions and mergers are inevitable. Over billions of years, spiral galaxies that wander into these crowded arenas are pulled and twisted by gravity, frequently merging with their neighbors. The result is that clusters become enormous cities of elliptical galaxies, the products of cosmic traffic jams and pile-ups that play out over eons. It is no coincidence that the largest elliptical titans are found at the centers of such clusters, where the wreckage of many galaxies has combined into one colossal whole. This grand process of galactic transformation is still unfolding. Even our own Milky Way is destined to experience such a fate. The Milky Way and the neighboring Andromeda galaxy are slowly drifting closer under their mutual gravity. In about 4 billion years, they will begin to collide and intermingle. As the galaxies intermingle, the familiar band of the Milky Way will warp and spread, filling the heavens with new patterns of starlight. Future beings might witness a breathtaking sight, a vast swirl of stars overhead as the two galaxies begin to overlap and merge. Over a long, slow dance of destruction and renewal, these two spirals will merge into one. Astronomers predict that the end result will be a vast, elliptically shaped galaxy, the future home of our Sun and its fellow stars, now within a shapeless titan born from what were once elegant spirals. Already, from Earth, the Andromeda galaxy is visible as a faint smudge in the night sky. In a few billion years, that smudge will grow larger and more luminous as Andromeda comes closer, eventually dominating the sky. As the galaxies intermingle, the gentle band of the Milky Way will distort, and great new patterns of stars will light up the night as our galaxy experiences the slow collision. It will be a gentle metamorphosis on the human timescale, but an inevitable one, written by gravity's hand. Over time, the two spirals will become one amorphous whole. Astronomers even have a name for this future merged galaxy. Sometimes it's whimsically called Milkomeda. It will mark the transformation of two spirals into a single giant elliptical, a process millions of years in the making. In the end, the serene elliptical galaxies we observe are monuments to that tumultuous past. From the wreckage of colliding galaxies, a new order arose, one without the graceful arms of a spiral, but possessing its own quiet symmetry. It is awe-inspiring to realize that the tranquil orb of stars we see today was forged by violence on a cosmic scale. Who would suspect that such tranquility was born from unimaginable cosmic havoc? The universe has a way of turning chaos into grandeur, and in the soft glow of an elliptical galaxy, the echo of ancient collisions lives on. Yet something fundamental has changed in that transformation. What was once a graceful rotating disk has become a more amorphous, random swarm of stars. In a spiral galaxy, the stars all orbit in the same direction and plane, like dancers following a well-rehearsed routine. But after a major merger, that orderly dance is broken. The new elliptical galaxy has no majestic spin uniting its stars. Instead, they move in all directions, a jumble of orbits without a single overarching rhythm. It is as though the collision stole the galaxy's rotation, leaving behind a cloud of stars with no memory of their former orderly motion. The difference is striking. Picture a figure skater spinning on ice, arms outstretched in a controlled, elegant rotation. That was the spiral galaxy before, spinning in space. The collision is like an abrupt interruption that throws the skater off balance, stopping the spin. The end result is a galaxy that no longer pirouettes in the cosmic dance. Without its spin, the galaxy drifts in a more aimless state, its stars wandering on whatever paths gravity dictates for them. Without a dominant spin to flatten it into a disk, the galaxy puffs outward. It takes on a more three-dimensional shape, often a sphere or an elongated ellipsoid. There are no distinct spiral arms or disk, just a hazy, featureless glow of starlight. The stars travel on inclined or eccentric orbits, filling the volume of the galaxy rather than circling in a thin plane. In telescopic images, an elliptical appears as an extended blob of light rather than a pinwheel, reflecting this lack of structure. From within such a galaxy, the view would be very different from that inside a spiral like the Milky Way. There would be no concentrated Milky Way band arcing across the sky, because the stars are not confined to a single plane. Instead, an observer would see stars in every direction, a more uniform expanse of distant suns surrounding them. The overall impression might be of a faintly glowing sphere of stars on all sides. Without the structure of spiral arms, the night sky of a planet in an elliptical galaxy would lack the dramatic starry stripe familiar to us, replaced by a gentler, all-sky glimmer of far-off old stars. If a spiral galaxy is like a calm, orderly whirlpool, an elliptical is akin to a swarm of bees around a hive. Each star, each bee, moves independently on its own route, yet all are loosely bound to the central gravitational well, the hive. There is constant motion, but it's chaotic in aggregate. To an outside observer, the elliptical galaxy may seem tranquil and unchanging, a steady glow, but internally it's teeming with stars flying this way and that, like a busy swarm with no single direction. Consider a single star within an elliptical galaxy. It may travel on a long, looping path that carries it close to the galactic core and then far out into the halo. Its orbit might be tilted at some arbitrary angle, not aligned with any common plane. Another star might dash around on a completely different path, perhaps more circular, but oriented at a steep angle to the first star's trajectory. Millions of stars follow millions of distinct routes. There is no concerted rotation to organize their motion, only the underlying pull of gravity, guiding each star on its individual voyage around the galaxy's center. A few ellipticals do retain a slight memory of rotation. They may spin slowly, or be somewhat flattened by residual angular momentum. These are the exceptions rather than the rule, and even they spin far more gently than a typical spiral galaxy. For the most massive ellipticals, however, almost all traces of the original spin have vanished. They are supported against collapse by the random hustle of their stars, rather than by any orderly rotation. It's a fundamentally different way for a galaxy to exist, one defined by dispersion and randomness, instead of a grand cohesive spin. This loss of a unified spin does more than change the galaxy's shape. It also goes hand in hand with deeper changes in the galaxy's life cycle. When galaxies collide, not only are their stars thrown into disarray, but their vast clouds of gas are violently stirred up. Much of that gas is either consumed in furious bursts of star formation or heated and driven outward. The end result is a galaxy largely emptied of the cool gas it once had. And with little gas remaining to form new stars, the galaxy begins to change in color and character, entering a quiescent phase of its existence. To lose a grand rotation is to gain a kind of peace. In shedding the whirlwind of its former spiral life, an elliptical galaxy finds a different equilibrium. It becomes a nearly symphonic randomness, a paradox of disorder that still manages to hold together in a stable form. One might wonder, without an overall spin to stabilize it, how does the galaxy not collapse inward? The answer is that the random motion of its stars effectively provides the support, like a thermal pressure inside a star, preventing gravitational collapse. This too is a marvel. Even without a guiding spin, billions of stars remain bound in a delicate gravitational ballet, their collective light steady and unblinking when seen from afar. Over time, the once turbulent merger remnant settles into a much quieter state. With its gas reservoirs depleted or expelled, the galaxy can no longer birth any bright young stars. Only the older stars remain, aging and cooling into reddish hues. Gradually, the galaxy's overall color shifts toward the warm glow of these ancient stars. Astronomers often refer to elliptical galaxies as red and dead. Red because of the dominance of old, cool stars, and dead because no fresh stars are being born anymore. The vigorous era of star formation has ended, leaving behind an immense geriatric society of stars. This contrast in color is apparent even in images of galaxy clusters. The ellipticals appear as yellowish or orange glowing blobs, while any spirals in the same cluster stand out with bluish hues from their young stars. The elliptical's golden light comes from countless aging suns, similar to or older than our sun, whereas spirals still sparkle with hot blue newborn stars in their arms. The difference is like comparing an autumn forest to a spring meadow, one dominated by the warm tones of maturity, the other by the bright colours of youth. The change is akin to a bustling city, gradually becoming a quiet town of retirees. In a spiral galaxy, hot blue stars are continually igniting the short-lived, brilliant youth of the stellar population. But in an elliptical, those youthful stars have long since burned out and vanished. No new bright blue stars rise to take their place. What remains are the golden and red stars, the survivors that burn steadily for billions of years. Their combined light gives the galaxy a softer, amber glow. It is a portrait of cosmic old age, a galaxy shining with the gentle light of its elders, with no new generation in sight. In this twilight era of its life, the galaxy simply glows quietly, content with what remains as time moves slowly onward. What future awaits such a galaxy? Having cast off the turmoil of youth, its destiny is to shine quietly and gradually fade, perhaps over trillions of years, as the cosmos around it continues to evolve. In many giant ellipticals, the last significant burst of star formation occurred billions of years in the past. Since then, the galaxy has been essentially coasting, illuminated by the accumulated glow of stars born in its youth. With no infusion of fresh gas to spark new stars, little changes in the galaxy's appearance, except a very slow dimming over the eons. The once turbulent heart that blazed with newborn suns has quieted to a steady, enduring luminescence. The galaxy still contains billions, sometimes trillions, of stars, but they shine with a steady, ancient light, each star a testament to the past brilliance. Over extremely long timescales, it will continue to fade, but very slowly. The smallest, dimmest stars will keep burning for trillions of years, ensuring the galaxy's light does not wink out entirely for an almost unimaginable span. In this sense, ellipticals are poised to be the last beacons of starlight in the far future universe, persisting quietly even as other more active galaxies exhaust themselves. It is a quiet existence, a far cry from the youthful fireworks of its star-forming days. Another hallmark of these aged galaxies is their rich population of globular clusters, compact swarms of very old stars that orbit the galaxy's core. A giant elliptical can be surrounded by thousands of such clusters, like a cloud of fireflies around a lantern. These globular clusters formed in the galaxy's youth and survived the tumult of collisions, remaining as orbiting outposts in the galaxy's halo. Their presence further testifies to the galaxy's advanced age and the long history of star formation that ended long ago. One reason for this prolonged quiet is the fate of the galaxy's gas during those violent interactions. When the two progenitor galaxies smashed together, vast clouds of gas collapsed rapidly into stars, consuming much of the available fuel in one great frenzy. The newborn massive stars lived fast and died young, exploding as supernovae that further heated and scattered the remaining gas. In addition, the central supermassive black hole, suddenly fed by torrents of infalling gas, likely became intensely active. It could have unleashed powerful winds or jets that swept out what little cool gas was left. By the end of this tumultuous period, the galaxy was effectively starved of the cold gas needed to form new stars. Even now, the galaxy isn't entirely devoid of gas, but what remains is thin and extremely hot. Many large ellipticals are embedded in halos of X-ray emitting gas, a tenuous plasma that envelopes the galaxy. This hot gas is like a faint, invisible atmosphere, too energetic to condense into clouds or spawn new stars. Instead of nurturing star formation, it merely envelops the galaxy in a silent, heated haze. This halo is another legacy of the earlier violence. The gas that wasn't flung away was superheated and trapped, forever prevented from cooling and coalescing into stars ever again. We can think of an elliptical galaxy in this phase as a cosmic ember, the aftermath of a once roaring fire. Long ago, its gas fueled blazing stellar bonfires, but now only the glowing cinders remain. The galaxy still shines, but softly, with the mellow radiance of red giants and old suns. Over extremely long periods, it will continue to fade, but its light will endure far longer than that of more active galaxies. These stars, many of them smaller and cooler than the Sun, can continue to shine for trillions of years. With no new stars to outshine them, they will gradually carry the galaxy's light into the far future, slowly dimming over almost unimaginable timescales. In this sense, ellipticals will be the ancient beacons of a distant future cosmos, glowing faintly while younger galaxies have long since burned through their fuel. In their golden twilight, these galaxies simply endure, witnesses to an earlier time, quietly glowing for eons. There is a gentle poetry in the stillness of an aging galaxy. Having spent its youthful fuel, the elliptical galaxy drifts into a long twilight. It glows with the accumulated light of its many veteran stars, each one a survivor from a more vibrant era. In that golden afterglow, the galaxy seems to be remembering its past, a silent chronicle of cosmic time, written in the enduring light of ancient suns. What future awaits such a galaxy? It has cast off the fervour of youth, and now simply keeps its quiet vigil. Its fate is to fade so slowly that the universe around it will change dramatically while it remains, a gradually dimming ember. Perhaps, trillions of years from now, its last faint red stars will still be shining, bearing witness to the passage of time long after more flamboyant galaxies have gone dark. For astronomers, an elliptical galaxy is an archive of cosmic history. Locked in the starlight of those billions of aging suns are clues to the galaxy's turbulent past. Every star carries a memory of the time and conditions under which it formed. By studying the colours and spectra of the light from an elliptical galaxy, scientists can decipher these memories. Each star in an elliptical galaxy is like a fossil embedded in rock, carrying information from a bygone era. By measuring the colours and brightness of these stars, astronomers can estimate their ages. A star with a slightly bluer tint might hint at being a bit younger, while a deep red hue indicates great age. But more than colour is used. They also dissect the galaxy's light with spectrographs, splitting it into a spectrum, a rainbow of wavelengths, to find chemical fingerprints. Within that light are signatures of elements like iron, oxygen, and magnesium, forged in earlier generations of stars. These spectral clues reveal how enriched the galaxy's gas became over time, and thus how many cycles of star birth and death the galaxy has seen. In this manner, astronomers essentially read the galaxy's autobiography written in light. Every feature in the spectrum, every color gradient across the galaxy, is a sentence or chapter recounting its past. If an elliptical galaxy's stars all turn out to be extremely old, say, formed around 10 to 12 billion years ago, it tells us that the galaxy had a furious early youth, forming most of its stars in one ancient epoch. On the other hand, if observers detect that some fraction of the stars are slightly younger, perhaps a few billion years junior to the oldest ones, that suggests the galaxy had a later chapter of star formation. Maybe there was a secondary burst, or the galaxy accreted a smaller system that brought in a bit of fresh gas. The presence of even a small younger population is a clue that the galaxy's evolution included multiple phases. For instance, an analysis of one elliptical galaxy's starlight might reveal two overlapping stellar populations, one extremely ancient and another just a couple of billion years younger. This suggests that while most of its stars formed in a primordial blaze, the galaxy later experienced a smaller renewal, perhaps when a gas-rich companion galaxy merged with it. Such details paint a richer story, indicating that even galaxies with predominantly old stars can have a complex formation history with multiple chapters. The chemical composition of the stars adds another layer to this cosmic detective work. Consider heavy elements. Astronomers call them metals, which accumulate over successive generations of stars. The more generations that have lived and died, the richer in elements like iron the next generation's composition becomes. In a galaxy that formed stars very rapidly in its early days, even those old stars can show surprising levels of heavy elements, because a rapid succession of supernovae enriched the environment. Conversely, if some stars have unusually low metal content, it could mean they were born before much enrichment took place, or perhaps they originated in smaller, metal-poor galaxies that later merged into the bigger system. By mapping these metallicity patterns across an elliptical, researchers can discern patterns. Often the core is filled with metal-rich stars, signifying a dense, intense early formation, while the outskirts might harbour more metal-poor stars, possibly the remnants of smaller satellites that were absorbed over time. All these pieces of evidence, ages, chemical makeup, spatial distributions, come together like tree rings or a cosmic jigsaw puzzle to form a picture of the galaxy's life story. In many cases, the narrative confirms what theory predicts. The largest ellipticals formed the bulk of their stars in a short, intense burst long ago, then spent the rest of cosmic history in relative calm. Yet there are always nuances revealed by the starlight fossils, perhaps a small uptick in star formation here, or an unusual chemical signature there, hints of minor mergers or late infall of gas that created a few last stars. Such details enrich our understanding, revealing that even these seemingly dormant galaxies had occasional flickers of activity after their prime. Still, the overarching theme remains. Elliptical galaxies are ancient survivors, and their very makeup, their stars, and their chemistry, encodes the story of a universe that was much more violent and active in its youth. In their quiet golden light, they carry the record of cosmic epochs long past, testifying to the dramatic events that forged them. By decoding this ancient starlight, we become time travelers in a sense. Each bit of data, each spectrum obtained from an elliptical galaxy, opens a window into the epoch of its formation. How much can we really know from mere light? As it turns out, quite a lot. With careful study, light becomes a messenger across time, carrying within it the secrets of how a galaxy came to be. The ability to reconstruct a galaxy's biography from the clues left in its light is one of science's quiet triumphs. It reminds us that even in the vastness of space and time, stories can be found and told. Stories of creation, transformation, and survival, all hidden in the faint glow of billions of distant stars. Yet the evolution of an elliptical galaxy does not freeze once it reaches its quiet adulthood. Even in their old age, these titans continue to change, albeit very slowly and subtly. The universe is filled with smaller galaxies and star clusters, and over time, a giant galaxy's gravity can draw these tiny companions in, pulling them apart and adding their stars to itself. In cosmic terms, the elliptical still feeds, slowly cannibalizing its surroundings. This gentle galactic cannibalism becomes another chapter in the life of the giant, showing that even in retirement, a galaxy can continue to grow. Imagine a small galaxy venturing too close to a much larger one. The Titan's gravity grasps the smaller galaxy and begins to pull it apart. Over hundreds of millions of years, the little galaxy unravels like a thread being pulled from a sweater. Its stars stream out in long, arcing tidal tails that wrap around the big galaxy's outskirts. Gas, if present, is siphoned away and absorbed. Eventually, the smaller galaxy's identity is entirely lost. Its stars now just another part of the elliptical giant's halo. This is galactic cannibalism in action, not a quick bite, but a slow, inexorable feast. The giant grows by consuming dwarfs, incorporating their stars into its own vast swath of light. We find evidence of this slow cosmic dining in the sky around us. Astronomers have detected faint rivers of stars looping around many galaxies, the lingering trails of devoured companions. Our own Milky Way has multiple stellar streams, including one from the Sagittarius dwarf galaxy that it has been stripping apart for billions of years. These long filaments of stars wrap around the Milky Way, clear signs of ongoing minor mergers. The Andromeda Galaxy, our nearest large neighbour, likewise shows a giant arc of stars in its halo, the remnants of a galaxy it devoured in the past. Such tidal streams are common signs of galactic meals in progress or long since finished. Elliptical galaxies, with their keen gravitational appetites, often display these telltale signatures as well. The shell-like structures and ripples we discussed earlier are one example, the debris of galaxies that ventured too close. In other cases, a giant elliptical's outer regions contain diffuse, ghostly clumps or streams of stars, marking where a smaller galaxy was torn apart and assimilated into the larger whole. One striking example of galactic cannibalism is observed in the Virgo cluster, about 55 million light-years away, where the colossal elliptical galaxy M87 resides. M87 is among the most massive galaxies known, and it did not attain that status without devouring others. Studies of its extended halo have uncovered traces of a medium-sized galaxy that M87 swallowed in the relatively recent past, in cosmic terms. Astronomers see distinct populations of stars and even a dense clump of globular star clusters in M87's outskirts that don't quite match the rest, likely the remains of that consumed galaxy. Over its lifetime, M87 has probably ingested dozens of smaller galaxies, growing more enormous with each meal. In effect, M87 is a giant formed by many contributions, a true galactic amalgam. This slow accumulation is thought to explain why some ellipticals have such massive, diffuse halos. Early on, an elliptical might have been much more compact, a dense ball of stars. But as eons passed and it cannibalized neighbors, it gained layers of stars in its outer regions. The galaxy swelled in size not through new star formation, but by adding stars from outside. What may have started as a compact, red nugget in the young universe could, after billions of years of mergers, become a giant with an extended envelope of stars. In a sense, these galaxies grow from the inside out. They establish their dense cores early, then build up their outskirts gradually through countless minor mergers. In the busiest environments like clusters of galaxies, cannibalism can go even further. Stars stripped from galaxies often end up wandering the cluster space itself, no longer bound to any single galaxy. This creates a faint ghostly illumination known as intracluster light, a soft glow permeating the space between galaxies, composed of orphan stars from past mergers. The central elliptical in a cluster may eventually gather some of these strays into its outskirts as well. In time, it can become a true behemoth, having consumed not just entire galaxies, but also loose stars originally from many sources. Even our Milky Way is not immune to this process. It is currently in the act of absorbing several small satellite galaxies. The Sagittarius dwarf is just one example of a victim being pulled apart. And in about 4 billion years, the Milky Way itself will engage in a much larger merger with the Andromeda Galaxy, as we noted earlier. When those two spirals collide and eventually settle, they will likely form one enormous elliptical galaxy. All the smaller pieces the Milky Way has consumed, and all that Andromeda has eaten, will be combined into that new system. Galactic cannibalism, it seems, is a natural part of galaxy evolution. It ensures that even in the universe's later epochs, galaxies continue to interact and change, knitting together into ever larger assemblies. Looking far ahead, one can imagine that trillions of years from now, a cluster's galactic inhabitants might merge into a single, enormous, elliptical galaxy. Over unthinkably long spans, repeated cannibal events could consolidate most of the cluster's stars into one dominant titan, while the universe's expansion will limit interactions at larger scales. Within gravitationally bound clusters, this gradual consumption may continue until only a few supergalaxies remain. It's a vision of the distant future, where the cosmic landscape simplifies, and ancient ellipticals reign supreme, having swallowed the last of their companions. Ultimately, the tale of galactic cannibalism speaks to the ever-changing nature of the universe. In nature, larger creatures often consume smaller ones, and galaxies are no exception. Is this a violent end for the smaller galaxy, or a form of rebirth as its stars join a larger community? Perhaps it is both, as those stars find new orbits within a grander structure. The giant ellipticals we see are the cumulative result of countless interactions, a slow weaving together of many galactic lives into one. It's a reminder that in the cosmos, nothing is truly static. The large are made from the small, and in time, today's galaxies will become the building blocks of tomorrow's giants. The majestic elliptical that reigns in a cluster is, in truth, a mosaic of many smaller histories merged into a single, enduring form. As surprising as it is to consider the distant future of these galaxies, equally astonishing are revelations about their deep past. Perhaps one of the most astonishing discoveries is just how early some of these elliptical titans emerged. By gazing deep into space, and thus far back in time, astronomers have found massive galaxies that were already old and quiet when the cosmos was only a few billion years young. The Hubble Space Telescope first hinted at these ancient giants lurking in the youthful universe, and now the James Webb Space Telescope is uncovering even more. It seems that not long after the very first galaxies formed, a few of them quickly grew into hefty ellipticals and then abruptly ran out of fuel to make new stars. To put this in perspective, picture the universe in its infancy. At a time when the cosmos was perhaps 20% of its current age, a mere few billion years after the Big Bang, there existed galaxies that already resembled cosmic senior citizens. In what was essentially the universe's childhood, these galaxies had the mass and star content of a fully grown giant, yet they were no longer forming new stars. They had grown up fast and retired early. The presence of such premature galactic giants challenges our understanding of galaxy formation. What special conditions could have allowed a galaxy to reach such maturity so fast? This question continues to spark debate and new research as scientists piece together the clues from those early times. It tells astronomers that under the right conditions, galaxy evolution can happen on surprisingly rapid timelines. Such early findings have been startling. Conventional wisdom held that galaxies in the first few billion years of the universe should be actively growing and forming stars. To find fully formed, massive galaxies already past the star-making phase, so soon after the Big Bang, forces astronomers to rethink how quickly structures can form. It appears that under the right conditions, the universe can build a galaxy in haste and quench it just as swiftly. How could an enormous, red and dead galaxy arise so soon? Scientists suspect that the unique conditions of the early universe enabled extraordinary growth spurts. In those epochs, matter was densely packed and gas more plentiful, possibly fueling quick star formation on a grand scale. One scenario envisions a single, massive collapse of a primordial gas cloud, essentially forming an elliptical galaxy in one monolithic event, a primordial fireball of star birth that exhausted its fuel in a flash. Another possibility is a rapid sequence of smaller mergers, numerous infant proto-galaxies crashing together in a short span, piling up into one massive system. In either case, the result would be similar. A galaxy that blazes with star formation very early on, then, having consumed or expelled its gas, settles into quiescence all before the universe is middle-aged. In cosmic evolution, this phenomenon is sometimes called downsizing. The observation that the largest galaxies seem to mature early and stop forming stars, while smaller galaxies continue to be active much later. In other words, the universe's giants live fast and die young in terms of star formation, whereas their smaller counterparts keep the star-forming flame burning longer. The discovery of these early massive ellipticals is a prime example of that trend. Tantalizing evidence supports aspects of these ideas. The early universe ellipticals identified so far tend to be remarkably compact, sometimes nicknamed red nuggets. They pack a tremendous number of stars into a small volume. This suggests their cores formed swiftly and intensely. Astronomers infer that these compact giants likely built their central bulk early, then gained additional mass over time through minor mergers, the sort of galactic cannibalism we've discussed. Essentially, they formed from the inside out, an initial core shining brilliantly in the young universe, followed by gradual growth of their outer regions as they assimilated smaller neighbors. By the present day, those once compact cores would have evolved into the huge, diffuse ellipticals we see in galaxy clusters, having collected layers of stars along the way. Indeed, the latest findings with new observatories hint that such galaxies may have appeared even earlier than previously thought. The James Webb Telescope has provided tantalizing evidence of massive, quiescent galaxies at even higher redshifts than we imagined. implying that some galaxies could have lived out their star-forming lives when the universe was only on the order of 1 billion years old. If these discoveries are confirmed, they represent galaxies that went from birth to burnout in the cosmic blink of an eye. Each one pushes the envelope of how quickly nature can assemble a galactic titan and then snuff out its star production. It's almost like opening a time capsule. Imagine peering back to a time when the universe was only a few % of its current age and spotting a faint, reddish smudge of light. Detailed analysis shows that smudge to be an entire galaxy, already massive, composed of old stars, and showing no signs of new star birth. It looks nothing like the immature proto-galaxies full of blue youngsters we might expect at that epoch, but rather akin to a miniature version of a present-day elliptical, an island of aged stars in a young cosmos. Discoveries like this leave astronomers both excited and puzzled, prompting the question, what special circumstances enabled such a galaxy to pack in so much mass so early and then fall silent? These first titans of the young universe serve as profound reminders of how rapid and dynamic cosmic evolution can be. In a sense, they are the elder statesmen of galaxies, appearing early and enduring long after their star-forming prime has passed. Their presence tells us that the universe, even in its youth, was capable of tremendous feats of creation, assembling and then exhausting giant galaxies in relatively short order. When we observe these distant ellipticals, we are looking at a kind of cosmic fossil record on the grandest scale. They bridge the era of primordial galaxies and the more mature cosmos we inhabit now, illuminating the continuity of the cosmic story. In the quiet light of these ancient giants, we see a reflection of an early universe that blazed with energy and then settled into an unexpected early calm. And yet, even after exploring their origins and long lives, elliptical galaxies still harbour mysteries. Deep in their cores lurk supermassive black holes, the silent engines that once might have blazed as quasars and now lie quiet, influencing their galaxies in subtle ways. Elliptical galaxies also interact with the wider universe. Their gravity lenses, distant light, and their ancient stars enrich space with heavy elements as they expire. There is more to uncover about these forgotten giants. As we continue our journey, we delve further into the secrets and significance of the elliptical titans, following the faint clues they offer about the cosmos at large. The story of these galaxies, it seems, is far from over. What does it mean that some galaxies grew up so early? It suggests that the universe wasted no time in crafting some of its giants, raising profound questions about the conditions of those first few cosmic dawns. In the chapters to come, we will continue to unravel these questions, each revelation about elliptical galaxies, from their dramatic births in fire to their slow retirements and surprising early appearances, deepens our understanding of the universe's grand narrative. The journey with these cosmic titans continues, and as we venture on, more revelations surely await in the gentle, mysterious glow of the elliptical galaxies. At the center of each massive elliptical galaxy lies a secret. Hidden in the diffuse starlight and invisible to our eyes, a powerful presence anchors the galaxy's core. This is a supermassive black hole, a gravitational abyss, millions or even billions of times more massive than our Sun. It is completely dark, allowing no light to escape its grasp. Yet its influence is anything but subtle, betraying its presence through the motions of stars and the rare but dramatic outbursts of energy from the galactic center. Astronomers long suspected something extraordinary lurked in the hearts of these galaxies. Peering into the nucleus of an elliptical galaxy, they observed stars whipping around an unseen object with astonishing speeds. The stars closest to the center move so fast that only an enormous concentrated mass could hold them in orbit. In galaxy after galaxy, careful measurements revealed the same pattern: a central mass, too great to be explained by any cluster of visible stars alone. The conclusion grew undeniable. Nearly every large elliptical galaxy harbors a supermassive black hole in its core. Like a hidden engine, this black hole's intense gravity quietly orchestrates the dance of countless stars around it. These black holes remain invisible directly, cloaked by distance and dust, but their gravity pulls on everything nearby. Imagine millions of stars in a bustling crowd near the galactic center. They swarm in all directions, some racing at hundreds or even thousands of kilometers per second, as if compelled by an unseen conductor. This is exactly what astronomers find. By studying the light from these central stars, they can map their velocities. The stars' rapid movements trace out the signature of a tremendous gravitational force, the unmistakable footprint of a central black hole. In this way, the darkness at the core makes itself known through the otherwise inexplicable speed of starlight swirling around it. Not all the evidence for these cosmic giants is indirect. Sometimes, a sleeping black hole awakens. If gas or stars stray too close, the black hole devours that matter and transforms into a ravenous, energetic beast. As matter falls inward, it heats up and glows, unleashing a storm of radiation. The galactic center, that was once faint, now blazes as a quasar or an active galactic nucleus. In the throes of feeding, the black hole can even hurl out narrow beams of plasma at nearly the speed of light. These jets drill through the galaxy and beyond, broadcasting the black hole's presence to the universe. Elliptical galaxies, often thought of as old and quiet stellar cities, sometimes harbor such dramatic activity. One giant elliptical galaxy might quietly house a dormant black hole, while another shows a jet shooting outward like a cosmic lighthouse beam. These jets can stretch for tens of thousands of light years, cutting through interstellar space. They are a striking reminder that a tremendous power lies at the galaxy's heart, capable of energizing matter and shaping its surroundings. In radio waves and X-rays, astronomers detect the glow of these jets and lobes far outside the galaxy, evidence that the central black hole is pumping energy outward. Even when quiet, the black hole influences its galaxy profoundly. Over millions of years, it can subtly regulate star formation by heating or expelling gas, ensuring that the galaxy remains dominated by its aging stars. The relationship between an elliptical galaxy and its black hole seems deeply intertwined. The largest ellipticals tend to have the most massive black holes, as if the galaxy and its dark heart grew together over cosmic time. It is a symbiosis forged in gravity. The galaxy provides the material, and the black hole provides the gravitational focus that locks the system together. Thus, every massive elliptical holds a dark secret at its center, a secret only revealed through the behavior of the galaxy's own stars and, on occasion, spectacular displays of energy. From the subtle, high-speed orbits of stars to the awe-inspiring jets piercing the galactic halo, these hidden black holes announce themselves. They are the silent architects of the galaxy's core, invisible engines that bind the elliptical galaxy together. In the grand, smooth glow of an elliptical galaxy, it is easy to overlook the tiny central region. But within that small volume lies a gravitational titan, an object so extreme that space and time warp around it. In this gentle cosmic nightscape, knowing that a supermassive black hole resides at the center of each galaxy lends an air of mystery. It is like finding out that a tranquil lake has unfathomable depths below its calm surface. The stars of the elliptical drift peacefully in their orbits now, Yet deep down at the nucleus is an object of almost unimaginable density and power. As our journey continues, we carry this knowledge that the smooth old galaxies we observe have, at their cores, these hidden hearts of darkness, silently influencing everything around them. And one such heart, in one particular galaxy, would soon offer humanity an unprecedented glimpse of a black hole's true nature. There is one elliptical galaxy whose dark heart became famous around the world. In the constellation of Virgo, about 50 million light-years from Earth, lies Messier 87, a colossal elliptical galaxy. For decades, astronomers knew something was extraordinary about M87's core. Early in the 20th century, telescope images revealed a mysterious luminous streak emerging from its center, a jet of energetic particles shooting outward. This jet, thousands of light-years long, signaled that a very powerful engine lurked in M87's nucleus. But what could drive such a cosmic fountain of energy? The answer, astronomers suspected, was a supermassive black hole, heavier than any found in our own galaxy. M87 sits as a heavyweight in the universe. It contains trillions of stars and a vast swarm of globular star clusters orbiting it. Yet, despite its immense scale, the galaxy's true power originates from a region smaller than our solar system at its center. There, a supermassive black hole named M87 star resides, with an estimated mass of 6.5 billion suns. For a long time, this black hole was inferred but not seen. Its presence was felt through the jet it emitted and the gravitational grip it exerted on surrounding stars and gas. M87 star was like a hidden monarch, ruling the galaxy from behind a curtain of darkness. All of that changed when an international team of astronomers decided to capture the unseeable. In a feat of scientific ingenuity, they linked radio telescopes across the globe to act in unison. This project, called the Event Horizon Telescope, essentially turned the entire Earth into one giant observatory. The goal was audacious: to image the immediate vicinity of M87's black hole and finally glimpse its silhouette. For several nights, in locations from mountaintops in Hawaii and deserts in Chile to the icy plateau of Antarctica, dishes swiveled in concert to collect the faint radio whispers coming from the distant galaxy. The data recorded was so vast that it had to be flown on hard drives to a central location for processing. Piece by piece, the team assembled a picture from the interference patterns, like solving a cosmic jigsaw puzzle. Night after night, the team carefully synchronized their observations, trusting that their combined efforts would reveal what no single telescope could see. When the image was unveiled, it transfixed the world. In the photograph, against a black background of space, floated a hazy ring of golden light with a dark center. We were looking at the shadow of a black hole for the first time in human history. The bright ring was emission from superheated gas swirling around the black hole's maw. The gravity was so intense that light itself was being bent into a circle around the darkness, and in the middle of that ring lay the silhouette, a round void where the black hole dwells, from which no light can escape to reach us. It was a sight both humbling and breathtaking, a direct confirmation that the predictions of Einstein's theory of gravity hold true, even at the very edge of a black hole. The image of M87's black hole was somewhat blurry to the eye, a fuzzy donut of light. But within that blur was profound clarity of understanding. The dark shadow measured about 40 billion kilometers across. To put that in perspective, it was larger than our entire solar system. If we could place the orbit of Neptune next to the black hole, the shadow would engulf it. This colossal black hole's surface, the event horizon, marked the boundary beyond which nothing returns. Seeing its shadow was akin to seeing a circular window cut out of the glowing background, an abyss outlined by light itself. What amazed astronomers and the public alike was not just the existence of the black hole, that was already expected, but the ability to see it. The level of detail required was mind-boggling. Capturing the image of M87's black hole has been compared to reading the date on a coin in Los Angeles while standing in New York. It required resolving tiny angles in the sky, on the order of tens of micro-arc seconds. Only by combining telescopes worldwide was this possible. The result was a triumph of human cooperation and technology, producing a picture literally from beyond the edge of visible reality. As we gaze upon the image, we are reminded of what lies at the center of this elliptical titan. The gentle golden ring belies the violence in that region. Orbital speeds nearing the speed of light, magnetic fields twisting, and matter being inexorably drawn inward. Occasionally, some of that infalling matter is diverted and flung outward as the great jet we see in M87. In fact, simultaneous observations showed the jet in other wavelengths, confirming it originates just outside that glowing ring, powered by the black hole's gravitational engine. The jet of M87, so prominent in optical and radio images, essentially arises from the very disk of bright gas we see encircling the black hole's shadow. For astronomers, M87's black hole image was like finally seeing the face of a familiar but elusive character in a story. We had long known of supermassive black holes, charted their influence, and even watched stars orbit our own galaxy's central black hole. But here, in M87, was a direct glance at one. It confirmed that inside an elliptical galaxy's core, nature can hide one of the most extreme objects known. The image also evoked a sense of connection. A giant elliptical galaxy in a distant cluster has a central heart that we could now visualize, linking that far-off place with fundamental physics that govern the cosmos. This achievement also underscored how special elliptical galaxies can be in revealing cosmic secrets. M87, with its enormous black hole, provided the perfect laboratory to test gravity under the most intense conditions. The fact that this black hole was so massive and relatively nearby made the observation feasible. In a sense, M87's quiet, fuzzy image became an icon, a symbol of humanity's ability to extend our vision to the invisible. It is a quiet image, just a ring of light, yet it speaks volumes about the turbulent forces at play and the deep well of gravity at the galaxy's core. With this picture etched into our collective memory, one can no longer look at a giant elliptical galaxy the same way. We now know, with direct evidence, that at least in M87, and likely in countless others, there is a glowing maelstrom at the center, swirling around a true dark heart. The shadows of those hidden titans are there, waiting in the darkness. In the case of M87, we have caught one in the act of casting its shadow. It leaves us to imagine similar scenes in other ellipticals across the universe. The black holes are usually invisible, but in M87, we saw one illuminated, a fleeting glimpse of the monster in the heart of an elliptical titan. As we leave M87's landmark contribution to science, we carry a renewed appreciation for what lies at the centers of these galaxies. We have seen the unseeable and confirmed that the silent giants at the cores of ellipticals are very real. Now that we understand the presence of these hidden monsters, we turn our attention to other subtle clues in elliptical galaxies' cores, signs written in the stars themselves, revealing how those central black holes have shaped their surroundings over time. Not all elliptical galaxy centers look the same. When astronomers first obtained high-resolution images of these galactic cores, they encountered a puzzle. In the largest and brightest ellipticals, the starlight did not keep increasing all the way to the center, as one might expect. Instead, it leveled off, forming a broad, dim plateau of light in the innermost region. It was as if someone had scooped out some of the stars from the very heart of the galaxy. These galaxies appeared to have shallow, nearly hollow centers. Astronomers call them cores. By contrast, smaller ellipticals often showed the opposite. Their starlight rose sharply into a steep peak at the center, indicating a dense crowd of stars right at the core. Those are said to have cusps, a bright pinpoint of starlight in their nucleus. This disparity between core and cusp galaxies hinted that different histories were at play. For giant ellipticals, the presence of a large, faint core was surprising. Common sense suggested that a supermassive black hole, with its intense gravity, should pull stars inward and create a tightly packed cluster around it. One might imagine the biggest black holes should be surrounded by the highest densities of stars. Yet observations revealed the opposite for the giants. The more massive the galaxy, and by extension, the more massive its black hole, the more underpopulated its center seemed to be. These huge galaxies have central regions that are unusually diffuse and fluffy, with far fewer stars than expected. Astronomers were left asking, where did all the missing stars go? The answer to this cosmic mystery turned out to be a tale of violence and upheaval. The biggest elliptical galaxies are believed to form through the collisions and mergers of smaller galaxies. When two mature galaxies of substantial size merge, each brings along its own central black hole. As the galaxies coalesce, their black holes eventually find each other and begin to orbit as a pair in the newly formed galaxy's center. This is where the drama unfolds. Two supermassive black holes spiraling around each other act like a gravitational wrecking crew. They stir the surrounding sea of stars with their combined gravity, flinging many stars out of the center. In a sense, the black hole pair behaves like a celestial blender or egg beater, mixing and throwing stars outward. Star by star, orbit by orbit, the duo clears out a gap around themselves, depleting the heart of the galaxy of much of its stellar content. Over time, some of those displaced stars are thrown entirely out of the galaxy, while others settle into wider orbits far from the center. By the time the two black holes eventually merge into a larger single black hole, they have carved out a much roomier core than the galaxy originally had. The result is exactly what we observe: a large elliptical galaxy with a low-density core, a visible scarceness of stars where a dense swarm might otherwise have been. The stars weren't destroyed, they were banished, victims of gravitational slingshots during the cosmic dance of black holes. The missing light in these cores, as astronomers call it, is essentially the footprint of that black hole scouring process. To test this theory, astronomers meticulously measured the brightness profiles of many elliptical galaxies and quantified how many stars were missing in the centers of the biggest ellipticals compared to what their light distribution would be without a core. They then compared that missing stellar mass to the mass of the central black holes, estimated from stellar motions or other means. The correlation that emerged was astonishingly tight, almost a one-to-one relationship. Galaxies with bigger black holes had proportionally larger deficits of stars in their centers. In other words, the amount of mass in stars cleared from the core closely matched the mass of the central black hole. The bigger the black hole, the emptier and more hollow the galaxy's center became. This near-perfect correspondence was a powerful, smoking gun that connected black holes with the formation of those fluffy, faint cores. Astronomers could finally see a direct link between the darkness at a galaxy's center and the dimming of its starlight. It's a striking thought. The bigger the black hole that an elliptical galaxy hosts, the more aggressively it has reshaped its own neighborhood, scooping out stars from the center. Instead of a teeming cluster of stars, the most massive galaxies present a relatively tranquil, even diffuse core. Floating through the center of such a galaxy, you might find it oddly spacious, with fewer neighbors than expected, as though you had wandered into a vast, dim cathedral of stars. The gravity of a once paired black hole duo has swept it clean. On the other hand, consider the smaller elliptical galaxies, those with cuspy centers. Their story is different. Many of these less massive ellipticals likely formed not through dry mergers of big galaxies, which tend to produce cores, but through processes that involved gas collapsing and forming new stars at the center. In a gas-rich merger or a late burst of star formation, gas can sink to the center of the galaxy and ignite a flurry of new stars. This creates a crowded cluster in the nucleus, a brilliant spike of light at the core. In these galaxies, the central black hole, while still present, did not have a partner of equal heft to scour out the core, or it grew gradually as gas funneled in over time. Thus, the stars were not expelled from the center. On the contrary, more stars may have been added to the innermost region after the galaxy's formation. The result is a steeply rising central brightness, the cusp, where the density of stars increases all the way to the innermost point that we can observe. The diversity of elliptical galaxy cores, some hollowed out, others densely packed, provides a kind of forensic record of each galaxy's past. A large, faint core strongly hints that the galaxy went through one or more major mergers in its history, during which central black holes combined and cleared the core. A tightly cusped center, conversely, implies a calmer history, or one where gas played a role in building up the nucleus after an earlier event. In some cases, we even find multiple peaks, or an elongated distribution of stars at the center, possibly indicating that a smaller galaxy's nucleus was swallowed and still survives as a distinct feature for a time. The centers of ellipticals hold memory of their violent or gentle pasts carved into their very structure. To envision this, picture an old, massive, elliptical galaxy in a galaxy cluster, a gigantic ball of stars that has cannibalized others over eons. Its core is broad and softly glowing, not blazing with central intensity, but strangely subdued. This is the mark of ancient violence, of black holes that met and merged, flinging away what once made the core bright. Now picture a relatively petite elliptical in a quieter corner of space. It still retains a tight sparkle at its center, a testament that it never endured a core-clearing cataclysm, and perhaps even experienced a burst of central star birth. Both types of galaxies share the elliptical name and general shape, but their hearts tell very different stories. In the grand scheme, these observations reinforce how deeply black holes are intertwined with their host galaxies. The same giants that sit unseen at the center can dictate the very distribution of stars around them. A supermassive black hole, especially in a pair, is not a passive passenger in a galaxy. It actively sculpts the galaxy's core structure. The missing stars in giant ellipticals are a silent testimony to the black hole's dramatic influence. And so, lurking within the diffuse glow of a giant elliptical's core is the record of a powerful event. The moment two black holes danced and became one, forever altering the galaxy's inner light. As we contemplate these hidden imprints in the starlight, we begin to see elliptical galaxies not as static, featureless collections of stars, but as dynamic systems with central chapters of drama. The core of an elliptical can whisper to us about collisions and mergers long past. Through careful observation and clever inference, astronomers have decoded some of that whisper, translating the dimming of starlight into a tale of black holes at play. It adds another layer of mystique to these galaxies. Beneath their smooth appearance lies evidence of a gravitational tempest that once raged at their centers. Now that we have uncovered these clues in the stars, we turn our gaze outward. There is yet another invisible presence enveloping these galaxies, the enigmatic substance known as dark matter. This unseen mass surrounds the galaxy and influences the motion of its stars. It is time to explore how dark matter dances through these titanic systems. Beyond the bright swarm of stars, an elliptical galaxy extends into darkness. Out in those dim outskirts lurks something enormous, yet invisible. A vast halo of dark matter. This dark matter does not shine or glow. It emits no light for our telescopes to capture. And yet, it outweighs all the stars in the galaxy, forming a hidden scaffold that holds the galaxy together. The stars we see are like dancers moving on a stage, but the stage itself, the gravitational foundation, is provided by this unseen mass. In the cosmic ballet of an elliptical galaxy, the visible stars are partnered with an invisible companion. They orbit faster and farther under the gravitational pull of dark matter, as if whirling to music we cannot hear. For a long time, astronomers could only speculate about the presence of dark matter in ellipticals. Unlike spiral galaxies, ellipticals don't have neat rotating disks where one can easily measure rotation speeds. Instead, their stars move in complex, randomized orbits, more like a swarm than a carousel. This made it challenging to detect the subtle influence of dark matter through stellar motions alone. Early studies sometimes even suggested that a few ellipticals could get by with little or no dark matter in their inner regions. But as observations improved and extended further out into the faint edges of these galaxies, the evidence for dark matter grew undeniable. The outer stars were moving too quickly to be bound by the gravity of the visible stars alone. There had to be additional mass, hidden mass, providing the extra gravitational pull. One striking piece of evidence comes from a phenomenon predicted by Einstein's theory of gravity: gravitational lensing. A massive object can bend the path of light, like a heavy lens in space. Giant elliptical galaxies, sitting in front of even more distant galaxies or quasars, can act as such lenses. Astronomers have found instances where a seemingly unremarkable elliptical galaxy produces remarkable effects on background light. Distant galaxies appear distorted into arcs, or even multiple images surrounding the elliptical. These are the signature of an intense gravitational field created by the galaxy's mass. Yet, when scientists tally up the mass contributed by all the stars in that galaxy, it falls short of what is needed to produce the observed lensing. The only explanation is a hefty contribution from dark matter enveloping the galaxy. In some Hubble Space Telescope images, one can see ethereal rings or arcs of light encircling an elliptical galaxy, the so-called Einstein rings, which vividly illustrate that the galaxy's true gravitational reach extends far beyond its visible stars. This gravitational lensing provides direct, visual evidence of the vast hidden mass enveloping the galaxy. Dark matter's dance with the visible galaxy is evident in other ways as well. Consider the hot gas that often fills the space around an elliptical galaxy. That gas, glowing in X-rays, is held in place by gravity. By studying the temperature and distribution of this X-ray emitting gas, astronomers can infer the depth of the galaxy's gravitational well. The gas is so energetic that without enough gravity, it would escape into space. The fact that massive ellipticals manage to corral huge envelopes of million-degree gas tells us their gravitational pull is extremely strong, stronger than what the visible matter alone could generate. The unseen dark matter halo provides the additional pull needed to keep the gas from flying away. In this way, X-ray observations independently reveal that something invisible, yet powerful, surrounds these galaxies. This method of weighing galaxies, independent of their starlight, confirms that a tremendous amount of mass lurks where we see only faint gas. It underlines the reality that an invisible halo is fundamentally shaping the galaxy's environment. To picture a dark matter halo, imagine a vast spherical cloud centered on the galaxy that extends far beyond the furthest stars. If the visible starlight of an elliptical tapers off around 100,000 light-years from the center, its dark matter halo might stretch several times farther out. At the edges of the galaxy, the stars and globular clusters gradually thin out into the void. Yet the dark matter continues onward, reaching deep into intergalactic space. The presence of dark matter means that the true mass of an elliptical galaxy is far greater than what our eyes perceive. An elliptical that we judge to contain, for example, 1 trillion suns worth of stars, might have several trillion more suns worth of dark matter in its halo. The luminous galaxy we photograph is merely the bright nucleus of a much larger, darker kingdom. This realization has transformed our understanding of galaxies from simple islands of stars into complex systems dominated by unseen matter. In a sense, the visible part of an elliptical galaxy is like the tip of an iceberg, with the vast bulk hidden below the surface. Except here, below the surface means hidden in the dark, beyond the reach of telescopes that rely on light. What does this dark halo do for the galaxy? It provides gravity to hold on to those fast-moving outer stars and the tenuous gas. It also serves as a gravitational glue during galactic encounters. When galaxies collide or interact, their dark matter halos pass through each other and exert additional forces that can help strip stars and gas out, or conversely keep them bound. In clusters of galaxies, the combined dark matter of many ellipticals forms a deep gravitational well that dictates the motions of all members. Individual ellipticals often sit at the centers of these clusters, swathed in not only their own dark matter, but also immersed in the cluster's dark matter environment. This makes them even more massive and influential than they would be in isolation. There is also a subtle dance occurring internally. As stars move within the galaxy, they respond to the gravitational potential shaped by dark matter. Over billions of years, the distribution of stars can even adjust slightly due to the presence of the halo. For example, some stars on the galaxy's outskirts might be slowed and pulled into tighter orbits, while others might be flung out into the halo, becoming part of a faint stellar halo that blends into the dark matter domain. Indeed, astronomers find that beyond the well-defined edge of an elliptical starlight lies a very faint glow. Stray stars that have been thrown into distant orbits, perhaps during past mergers. These stars act as tracers of the unseen mass. By tracking their motions, astronomers can map the dark matter's influence far from the galaxy's center. In this way, even without seeing dark matter directly, the behavior of these outlying stars provides a roadmap to the invisible halo. It is a subtle but powerful technique to unveil the otherwise hidden mass. In recent years, using both giant telescopes and computer simulations, scientists have come to visualize the dark matter halo not as a rigid sphere, but as a dynamic structure. It can be lumpy or elongated, sometimes stretched by the same forces that cause tidal streams and shells of stars. While we cannot see dark matter directly, its distribution can be inferred by its gravitational effects. Techniques like weak gravitational lensing, a statistical distorting effect on background galaxies, allow astronomers to map out the average dark matter halo around massive ellipticals. The result consistently shows that a halo extends well beyond the visible bounds and carries a mass many times that of the visible galaxy. All this means that an elliptical galaxy, smooth and self-contained as it may appear in visible light, is actually the visible core of a much larger invisible system. The dance between the stars and dark matter is a slow and graceful one. Each star moves under the combined gravity of all other matter, most of which it cannot see. This hidden partner influences every orbit, every cluster of stars, and even the fate of gas and dust. It is a reminder that in the universe, what you see is not always all there is. In fact, it's often just a fraction. For the ellipticals, the forgotten giants of starlight, their true might and mass lie in this dark component, silently guiding their evolution. Having illuminated the invisible halo that envelops these galaxies, we can appreciate how deep and massive an elliptical truly is. But the story of an elliptical galaxy is not just one of gravitational forces and invisible matter. There is also a vivid tale told by the energetic environment within and around them, particularly the hot, X-ray glowing gas that envelops their halos. To witness that side of these galactic titans, we need to tune our vision to the X-ray band, where another hidden aspect of ellipticals comes to light. If we could see an X-ray light, we would notice a faint, expansive glow around many elliptical galaxies. These giants are not surrounded by empty space, but by enormous halos of extremely hot gas. This gas forms a kind of invisible atmosphere for the galaxy, heated to temperatures of millions of degrees. At such high temperatures, anywhere from 1 to 10 million Kelvin, the gas is fully ionized plasma, emitting X-rays as it slowly cools. To our eyes, the halo is invisible, but X-ray observatories like Chandra and XMM Newton reveal a cocoon of diffuse radiation enveloping the galaxy. It is as though each massive elliptical sits at the center of a gently glowing furnace, its outer reaches radiating a soft X-ray light that betrays the presence of this hot medium. The existence of these X-ray halos came as a surprise when first discovered. Elliptical galaxies were once thought to be mostly bereft of gas, having used up or lost the cooler gas needed for star formation. Yet, when X-ray telescopes were turned toward some of the brightest ellipticals, they detected this extended emission. For example, the isolated giant galaxy NGC 4555 was found to be embedded in a cloud of gas at temperatures on the order of 10 million degrees. Far from being empty, the space around the galaxy was filled with an extremely tenuous but incredibly hot atmosphere. This discovery showed that even red and dead galaxies, those no longer forming stars, can possess significant reservoirs of gas, only in an unexpected form, not cold and star-forming, but searingly hot and thin. The hot gas in an elliptical's halo is exceedingly diffuse, with densities much lower than any air we're familiar with. A cubic centimeter of this plasma might contain only a few particles. Despite its thinness, the sheer volume of these halos means they contain a substantial mass of gas. How did the gas get so hot? Astronomers believe that as gas fell into the deep gravitational potential of a massive galaxy, it was shock-heated to high temperatures. Some of it might be the accumulated breath of aging stars. Over time, numerous red giant stars and supernovae eject gas into the galaxy's surroundings. In a smaller galaxy, that gas might cool and form new stars, but in a giant elliptical, The gas finds itself in a deep gravitational well and gets compressed and heated instead. Once heated to X-ray temperatures, it stays too energetic to condense into new stars. Thus, the galaxy retains a halo of old, enriched gas, laden with elements like iron and oxygen from past stellar generations, held aloft in a hot, tenuous state. In galaxy clusters, where ellipticals are most commonly found, the distinction between a galaxy's own gas halo and the cluster's general atmosphere blurs. The whole region is pervaded by X-ray emitting gas, and individual galaxies swim within this hot sea. A massive elliptical at a cluster's center often sits in the densest part of this intracluster medium. Its halo merges into the cluster's gaseous environment, extending hundreds of thousands of light years. In such cases, it can be hard to tell where the galaxy's halo ends and the cluster's begins. They become one continuous, glowing cloud. In smaller groups of galaxies, similarly, a big elliptical can be surrounded by group-wide hot gas. Even an isolated elliptical, however, can maintain its own X-ray halo, confined by the galaxy's gravity. The presence of gas at such extreme temperatures is a sure sign of a substantial gravitational field. Only a truly massive object can prevent gas at millions of degrees from dispersing into space. The interplay between the hot gas and the galaxy itself is fascinating. This gaseous halo is not static. It slowly sinks inward under gravity, and in doing so, it can cool over time. If left to itself, the gas in the central regions of a cluster or galaxy's halo would eventually cool enough to condense into cooler clouds and potentially form new stars. Yet, astronomers observed a puzzling fact. In many big ellipticals, especially those at cluster centers, the gas doesn't seem to cool as much as expected. Something is heating it, preventing the predicted cooling flow from turning the hot halo into a burst of new star formation. The prime suspect for this heating is the galaxy's central supermassive black hole. Though the black hole might be quiet at times, it periodically erupts with energy when enough matter accretes onto it. This energy, often released in the form of powerful jets and outflows, injects heat into the surrounding gas. It seems the black hole acts like a cosmic thermostat, releasing energy when the gas cools too much and thus keeping the halo hot. Chandra X-ray images have revealed dramatic evidence of this feedback process. In some giant ellipticals, one can see vast bubble-like cavities carved out of the X-ray gas, regions where the X-ray emission is dim, because the hot gas has been pushed aside. These cavities correspond to places where jets from the central black hole have inflated lobes of radioplasma, displacing the hot gas. Over time, the bubbles buoyantly rise outward and eventually dissipate, releasing their energy into the halo. The result is a gentle but persistent heating of the gas, like a simmering pot that is kept from cooling down completely. In the Perseus cluster, for example, the central elliptical galaxy, Perseus A, shows huge ripples and bubbles in its X-ray halo, testament to repeated outbursts from its black hole. In M87, the central galaxy of the Virgo cluster, astronomers have observed similar cavities and shock fronts in the hot gas, aligning with the activity of its central engine. These findings illustrate a cosmic balancing act. The hot gas tries to cool and sink, but the black hole's intermittent eruptions pump energy back into it, preventing a catastrophic cooling collapse. The X-ray halos also serve as a kind of diagnostic tool for astronomers. By analyzing the spectrum of the X-rays, essentially the color of this high-energy light, scientists can determine the temperature and even the composition of the gas. They find that the gas around ellipticals often contains heavy elements forged in stars and blown out by supernovae, confirming that the halo is enriched by the galaxy's stellar history. The temperature profile, how hot the gas is at various distances from the center, tells us about the balance of cooling and heating, and thereby the influence of both gravity and black hole feedback. In effect, the hot halo retains a memory of the galaxy's past, its formation, its star-forming era long ago, and its recent bursts of nuclear activity. From a more serene perspective, one can imagine this halo as an enormous, glowing aura around the galaxy, an ethereal counterpart to the visible galaxy. If we were floating in space near a giant elliptical, our eyes wouldn't see this halo, but a sensitive X-ray telescope would reveal a subtle radiance permeating the darkness. That halo would gradually brighten toward the center, where the gas is denser and hotter, and fade out into space at the edges. It is a beautiful concept. Even in a galaxy that to optical eyes appears old, quiet, and done with its youthful fireworks, there remains this vast, high-energy envelope humming with thermal activity. In the life of an elliptical galaxy, the X-ray halo is a crucial chapter. It speaks of gravity's grip and the ongoing dialogue between the galaxy's heart and its surroundings. The hot interstellar medium is both a reservoir of materials and a regulator of the galaxy's evolution. It can fuel the central black hole if some of it eventually cools and drifts inward, yet that same black hole can prevent the bulk of the gas from ever cooling too far. This dynamic ensures that elliptical galaxies, once they reach a certain size, remain dominated by old stars and do not sprout new ones easily. Their hot halos see to that. The energy locked in those halos is immense, and over billions of years they will slowly dissipate their heat into space or settle into equilibrium under the gentle push and pull of heating and cooling. With this portrait of an elliptical galaxy's glowing halo in mind, we not only appreciate the galaxy's visible stars, but also its extended atmosphere of X-ray fire. These halos underscore the scale and power of ellipticals. Their gravity can corral gas at temperatures that defy imagination, and their central black holes wield influence across hundreds of thousands of light years. And as we consider such evidence of past turmoil and present equilibrium, we should also look for the scars of earlier collisions that might still linger around these galaxies. Indeed, if we peer into the faint outskirts of ellipticals in visible light, we often find enigmatic shells, ripples, and streams of stars, the lingering relics of ancient violence that hint at how these titans grew through mergers. The seemingly tranquil outskirts of an elliptical galaxy can hide evidence of a tumultuous past. With the right depth of observation, long exposures on large telescopes, astronomers have discovered faint structures lacing the halos of many ellipticals. These structures often take the form of delicate shells, ripples, or filaments of stars. They appear as subtle brightness enhancements, curving arcs, or faint streaks in the darkness, barely distinguishable from the night sky. To the imaginative eye, they resemble the reverberations of a cosmic collision. Much like ripples on a pond after a stone has been thrown, the stars of a disrupted galaxy can ripple through their new host for eons. Shells are one of the most striking of these relics. They are faint, concentric arcs of starlight that often appear on both sides of a galaxy, as if the galaxy were encased in ghostly rings. Typically, shells are very faint. You wouldn't notice them in a casual image, but with enhanced imaging, multiple shell-like edges emerge at various radii. They look like layers wrapping around the galaxy's outskirts. Astronomers think shells form when a smaller galaxy, often a spiral or dwarf, merges head-on with a larger elliptical. The stars of the smaller system, flung out by the violence of the merger, begin to oscillate through the larger galaxy. As they reach the farthest points of their orbits and slow down before falling back inward, they pile up, creating an overdensity, a shell. Each shell marks a place where a group of stars has come to a temporary halt before turning around. Over time, those stars move back toward the center, then out again on the opposite side, forming another shell. A single merger can produce a whole series of shells, each corresponding to stars on a particular orbital path. The result is a set of ripple-like patterns that gradually widen and fade with distance. Ripples, a similar phenomenon, are more subtle waves in the starlight. They might not form sharp-edged structures like shells, appearing instead as gentle undulations in the galaxy's brightness. Ripples can be the outcome of less direct interactions, perhaps a smaller companion grazing the outskirts of an elliptical, stirring its stars slightly without completely merging. In some cases, what we call ripples could be shell structures viewed at odd angles, or just less pronounced due to the specifics of the collision. Regardless of their exact origin, ripples convey the same message. The galaxy hasn't always been calm. It has been disturbed by gravitational encounters. Then there are tidal streams, long trails of stars that extend out from a galaxy. Unlike shells and ripples, which are relatively symmetric, streams often have a one-sided, tail-like appearance. They form when a small satellite galaxy is torn apart by the tidal gravity of a larger galaxy. Stars from the hapless satellite get stretched out along its orbital path, leaving a trailing stream that can wind around the main galaxy like a faint thread. Sometimes, these streams are the only visible sign that a dwarf galaxy is being cannibalized. In other instances, a stream can be the remnant of a past merger, slowly dispersing over time. Streams are essentially the tattered remains of galaxies, drawn out into the depths of space. One of the most famous examples of an elliptical with such telltale markings is Centaurus A, a peculiar galaxy well known for its active nucleus. Centaurus A is an elliptical that sports a conspicuous dark band of dust across its middle, the leftover of a spiral galaxy it devoured, and around it, faint shells and streams of stars have been detected. These features, combined with its powerful radio jets, paint a dramatic picture of a galaxy that has both feasted on a companion and is powered by a restless black hole. It vividly demonstrates how a large elliptical can incorporate a smaller galaxy and bear the marks of that merger. While Centaurus A is somewhat unique in its prominent dust lane, many other ellipticals without obvious dust still show faint stellar shells and ripples when imaged deeply. For instance, the galaxy NGC 3923 reveals dozens of shells encircling it, a spectacular record of repeated cannibalism. Each shell in such galaxies hints at a time in the past, perhaps within the last few billion years, when a smaller system was incorporated. These structures are, in a sense, fossils of the galaxy's formation history. Elliptical galaxies grow, as we have seen, not only by forming stars in place, but significantly by merging with and accreting other galaxies. Every major merger can leave behind traces for a while. Eventually, after billions of years, the stars from a merger will scatter and smooth out, becoming part of the general halo of the galaxy. But in the interim, before those remnants completely dissipate, we can catch them as distinct features. The persistence of shells and streams suggests that some of these encounters happened in relatively recent cosmic times, because the structures haven't fully dispersed yet. By studying their shapes and distributions, scientists effectively perform cosmic archaeology, reconstructing the events that built the galaxy. Certain patterns might indicate whether the galaxy swallowed one large companion or many smaller ones over time. Imagining a merger that leads to these patterns isn't difficult. Picture a smaller galaxy plunging into a larger one. As their stars intermix, gravity plays tug-of-war on entire stellar populations. The smaller galaxy's stars are flung into wide orbits around the giant galaxy. Some dive through the core and emerge out the other side, only to slow and fall back again, creating oscillations. Others get left behind in elongated loops. In time, this chaos settles into artful patterns, arc-like shells spaced at intervals, each a congregation of stars paused at the edge of its orbit, ripples of light marking where waves of stars passed through, or a tidal streamer wrapping around, slowly dispersing, but still coherent enough to trace the path of the long-lost companion. It's a beautiful visual testament to the violence that occurred. These remnants of cosmic violence tell us not only about individual galaxy histories, but also about the assembly of the universe on the largest scales. Large ellipticals often sit at the centers of galaxy clusters or groups, having grown by consuming many smaller neighbors. The shells, ripples, and streams are the records of those meals. In a way, they are like the growth rings of a tree, or the stratified layers in a cliffside. Each one encodes a chapter of the galaxy's life story. By studying them, astronomers have confirmed that hierarchical merging is a key process in galaxy evolution. They've even found stars in some streams that once belonged to the disk of a spiral galaxy, now strewn out, evidence of a spiral to elliptical transformation in progress. In time, these stellar echoes of past mergers will fade away. The stars will complete many orbits, the patterns will smear out, and the elliptical will regain a more featureless halo. But until then, we have a chance to witness the aftermath of those collisions. It's a reminder that even the oldest, most seemingly quiescent galaxies carry memories of a more chaotic youth. All we have to do to uncover those memories is look deep enough into the faint twilight of their halos. There, the ghosts of past galaxies linger in starlight, telling stories of collisions and cannibalism in a bygone age. Even galaxy clusters, those mighty cities of galaxies, are not the final, immovable structures in the universe. They too feel the inexorable pull of gravity on still larger scales. Over time, clusters can draw together, and when they do, the result is one of the most titanic events in the cosmos, a collision of galaxy clusters. These are cosmic collisions on a scale that dwarfs the mergers of individual galaxies. Here, not just stars or nebulae collide, but whole clusters with all their galaxies, gas, and dark matter engage in a slow, colossal encounter. Imagine two immense clusters, each one millions of light-years across, and containing thousands of galaxies, drifting toward one another across the expanse of space. For billions of years, they have been moving along the threads of the cosmic web, and now fate brings them together. As they draw near, gravity accelerates them to incredible speeds, thousands of kilometers per second. From a great distance, their approach would appear silent and stately, like two giant clouds merging in a dark sky. But up close, the violence is profound, albeit stretched over hundreds of millions of years. There is a paradoxical grace to it, a slow-motion crash of unimaginable scale. When the clusters begin to interpenetrate, their constituent galaxies largely pass by each other without direct collisions. Galaxies are tiny points relative to the vast distances between them, so the chance of two stars from different galaxies smashing together is extremely low. Most of the galaxies simply sail through the collision zone, their paths deflected by gravity, but their stellar populations intact. In fact, an observer on a planet inside one of those galaxies might not immediately realize a cluster collision was happening at all, because the nearest stars and their motions would remain dominated by their own galaxy. Yet the cluster as a whole would be undergoing drastic changes, visible only on the grandest scales. The first truly violent interaction occurs between the cluster's hot gas envelopes. Each cluster's intracluster medium, that vast X-ray glowing atmosphere, cannot avoid collision. As the clusters slam together, these gaseous halos crash into one another head-on. Imagine two enormous clouds of hot gas, each moving at thousands of kilometers per second, meeting like colliding storm fronts. The result is a shockwave of unimaginable scale. Enormous, billowing fronts of compressed, superheated gas surge through the merging clusters, analogous to the sonic boom of a supersonic jet, but spanning millions of light years. The gas, already at tens of millions of degrees, is heated even further in the shock, briefly creating regions so hot they shine even more brightly in X-rays. In that moment, the intracluster medium experiences a jolt of energy that sends ripples across the newly forming combined cluster. If we could watch such a collision in extreme slow motion, we would see a breathtaking sequence. As the two cluster cores penetrate each other, a bright, bow-shaped shock front forms in the intracluster gas. A sweeping curtain of X-ray brilliance, marking where the gas is piling up and searing itself even hotter. Behind this shock front, turbulent eddies start to swirl as the gases of both clusters intermingle and churn. The galaxies, mostly untouched by direct impacts, begin to fly on new trajectories, some flung out to larger distances by the changed gravitational landscape. A few galaxies might even be catapulted toward the outskirts of the new cluster, or beyond, if they gain enough speed in the gravitational upheaval. For hundreds of millions of years after the initial core passage, the cluster will ring with the after effects, gas oscillating and sloshing due to the enormous disruption, and galaxies settling into new orbits in the merged gravitational field. One famous example of such an event is quaintly named the Bullet Cluster. In this system, two clusters collided, and the aftermath has been freeze-framed by telescopes. The smaller cluster's hot gas was stripped away by the collision, left trailing behind like the fiery wake of a bullet as it passed through the larger cluster's gas. In X-ray images, we see this wake as a bright, arrowhead-shaped cloud, the bullet racing away from the impact site. But what about the galaxies and dark matter from that smaller cluster? Fascinatingly, they did not slow down as the gas did. They surged ahead of the wreckage. The galaxies, being relatively collisionless, simply continued on their way, and the dark matter, equally collisionless, followed suit, clustering around those galaxies as an invisible companion just as before. Astronomers were able to map where the mass in the bullet cluster ended up by using gravitational lensing, the technique we discussed earlier. The lensing revealed that most of the mass, dominated by dark matter, had moved ahead of the slowed gas. In other words, the energetic crash so visible in X-rays was primarily affecting the normal matter, the plasma, while the dark matter slipped through without slowing, interacting only via gravity. This observation provided some of the clearest evidence yet that dark matter is a separate component, not impeded by shocks or pressure the way ordinary gas is. It passes through the chaos largely unhindered, while the gas suffers the shock and lags behind. The bullet cluster collision, therefore, serves as a dramatic cosmic laboratory, separating the seen from the unseen and confirming the existence of dark matter in a truly spectacular fashion. Cluster collisions also influence the galaxies within them, in indirect but significant ways. In the turmoil, some galaxies that were comfortably orbiting in one cluster suddenly find themselves in a denser environment with unfamiliar new neighbors. Increased gravitational encounters can disturb their shapes or trigger brief flurries of star formation, as cold gas in those galaxies is jolted by the violence. Other galaxies might lose whatever tenuous gas they had left, swept out by the wind of the intracluster gas stirred into motion. The overall effect of a massive merger is to scramble the cluster's contents and then reassemble them in a new configuration. In the merged cluster, the galaxy population may be altered, perhaps showing an even higher proportion of ellipticals if spirals were quenched, and often boasting a fresh central giant if two big galaxies at the cluster centers have coalesced into one. Indeed, at the center of the new cluster, a brightest cluster galaxy often emerges, possibly born from the merger of the two former central ellipticals, now combined into an even more massive titan. As the chaos subsides over eons, the two clusters become one larger cluster in a state of relative calm. The hot gases eventually settle into a new equilibrium, forming a larger, even brighter X-ray halo that envelops the merged system. The galaxies, now all bound in a deeper common gravitational well, carry on their orbits, though some may bear subtle scars of past encounters. And at the core of the merged cluster, an enlarged central galaxy takes its throne, a colossus perhaps even more dominant than either progenitor, having swept up new stars and even whole galaxies that were funneled toward the center during the merger. From start to finish, a cluster collision is a slow cosmological dance, graceful in its inevitability, but ferocious in its effects. It underscores the fact that structure in the universe builds hierarchically. Small systems merge into bigger ones. Just as individual galaxies come together to form clusters, clusters themselves can unite into superclusters and colossal conglomerates. In these grand collisions, we witness the universe's ongoing construction project, as gravity takes disparate pieces and molds them into larger wholes. The shock waves from cluster mergers can extend for many millions of light years, injecting energy that will keep the intracluster gas simmering for eons to come. In some collisions, the stirring of the gas and the injection of turbulence also amplify magnetic fields and accelerate particles, leading to giant diffuse radio halos that glow with faint radio waves long after the merger. In fact, astronomers often observe such giant radio halos or elongated relic arcs around merging clusters. Unlike the concentrated radio jets from individual galaxies, these halos stretch for millions of light years across the cluster, energized by the turbulence and shock-accelerated particles that the collision leaves behind. They are invisible to human eyes, but radio telescopes reveal their soft glow, which gradually fades over time. These halos and relics are like ghostly echoes of the collision, fading whispers of the violence that once took place. Yet, amid all this grandeur and upheaval, one can also find a certain cosmic order. After sufficient time, the merged cluster relaxes into a stable configuration under gravity's guidance. The ellipticals we have followed, those old red star cities, persist, now as part of an even larger community. They continue orbiting within their new cluster home, perhaps slightly changed, but largely unbroken, testaments to their incredible resilience. In fact, these hardy ellipticals often end up even more dominant in the post-merger cluster, as star formation in any remaining gas-rich galaxies has been quenched, and the turmoil of the merger tends to favor galaxies that can endure the violence. The elliptical titans thus continue their reign in the new kingdom that forms, shining on as the ancient beacons of their cluster. Our exploration of elliptical galaxies in the context of clusters has revealed them as both spectators and protagonists in these enormous events. They survive cluster-wide cataclysms and often even grow because of them, maintaining a vice-like grip on the title of brightest and most massive members. From the calm centers of clusters to the dramatic collisions that reshape the cosmic landscape, ellipticals have proven to be steadfast keepers of cosmic history, holding memories of all that has transpired around them. And so, having delved into the realm of clusters and witnessed the might of elliptical galaxies in these densely populated arenas, we look onward. As our journey continues, we will uncover how these monumental galaxies fit into the grand design of the cosmos beyond the cluster environment. There are larger arenas and deeper mysteries where the elliptical titans play their part, and we are not yet done with their story. time flows onward, and the cosmos calms from its youthful fervour. The great elliptical galaxies, once forged in fire and tumult, now enter an era of quiet. Their once brilliant star nurseries have gone dark, and no new suns kindle within these ancient halls of stars. Only the soft, steady glow of aged starlight remains, suffusing each giant galaxy with a gentle, golden haze. Seen from afar, an elliptical galaxy is a hazy, rounded glow against the darkness, lacking the graceful spiral arms or bright nebula patches found in younger galaxies. There are no swirling bands of dust or newborn stars tracing patterns in these giants. Instead, the light is smooth and diffuse, brightest at the core and gently fading toward the edges. The colour of this light is a subtle red gold, the telltale hue of ancient stars that have long since left their blue youth behind. Within these galaxies, the stars themselves are the elders of the cosmos. Nearly all of the bright blue giants that once blazed here have long since burnt out or exploded, their remnants now cooling as tiny embers. What remain are countless yellow and red stars, many as old or older than the sun, spread across a vast volume. In the core, they crowd together in a dense, ancient city of light. Farther out, swarms of globular star clusters pepper the halo, each cluster an antique treasure chest of hundreds of thousands of very old stars. This is a universe of elder suns, a realm that has witnessed the passage of eons in quiet dignity. Among the multitude of aging stars are also the ghosts of those that have already burned out. Scattered throughout the galaxy lie uncountable white dwarfs, the pale, fading embers of once radiant suns, quietly cooling for eternity. Here and there, a neutron star may spin in the darkness, the dense remnant of a supernova from ages past, perhaps blinking as a faint pulsar lost among millions of other faint lights. Even black holes from ancient massive stars lurk unseen in this stellar metropolis. These relics, too, are part of the giant galaxy's population, contributing to its mass, if not its light, and reminding us that the galactic decline is well underway. Yet one vital ingredient for rejuvenation is missing from these colossal galaxies: the cold gas that fuels starbirth. Long ago, whatever reservoirs of hydrogen they once had were either used up in furious bursts of early star formation or blown out by ferocious winds. Today, only trace amounts of gas and dust linger within ellipticals, and what remains is often too warm and too thin to clump into new stars. In these quiet giants, the star-making factories have shuttered their doors. There are no shining nurseries left, only memories of creation that happened billions of years before. In many ways, the story of elliptical galaxies mirrors the broader story of the universe. Most of their stars were forged during the universe's youth, when cosmic star formation was at its peak. Back then, gas was abundant, and galaxies grew rapidly, often through violent mergers that sparked brilliant bursts of new stars. Now, with the cosmos having settled into a calmer Middle Age, these ellipticals serve as majestic relics of that bygone era. Their faded glow is a reminder that the age of blazing starbirth has largely passed, and a quieter epoch has taken hold among the largest galaxies. With no new fuel to spark youthful stars, the giants settle into a long twilight. Their collective radiance will slowly ebb as each generation of stars ages and expires. Over millions and billions of years, the galaxy's overall light diminishes almost imperceptibly, like the embers of a once roaring fire gradually cooling. It is a gentle decline, not a sudden death, a slow dimming that will carry on for as long as there are stars left to shine. In this cosmic retirement, the elliptical titans preside in silence, their days of glory behind them, their future a gradual fading into darkness. Imagine yourself on a world orbiting one of those old stars, deep inside an elliptical galaxy. The night sky above would be unlike the view from our Milky Way. Instead of a ribbon of a bright Milky Way band, you'd see a gentle smattering of starry light in every direction. In the densest regions near the galaxy's heart, the sky might never be truly dark at all. Countless stars would dot the heavens, their combined glow casting a faint perpetual twilight. There would be no colourful nebulae shining, no bright young clusters blue-white against the dark. Only the steady burn of ancient suns surrounding you like a quiet, cosmic ocean of light. Despite their hushed state, these galaxies remain titanic in scale and influence. A giant elliptical can contain far more stars than a typical spiral galaxy, packing the mass of several Milky Ways into a single, sprawling sphere of stars. In sheer size and gravitational pull, they still dominate their cosmic neighborhoods. They are like ancient emperors. Even in retirement, their presence is enormous, their gravity shepherding surrounding galaxies and hot gas. The decline of star formation has not diminished their stature. Only their youthful clamour is gone, leaving silent giants that still rule the realm by their sheer mass and legacy. To the casual stargazer, an elliptical galaxy might seem unremarkable, just an oval smudge of light in the telescope, lacking the grand spiral design or glittering newborn stars that draw the eye. Yet within that unassuming glow lies a rich archive of cosmic history. Each old star carries the chemical fingerprints of an earlier universe, and the motions of these stars preserve the memory of ancient collisions and mergers. In their silence, ellipticals have much to tell. Astronomers peering into their light can piece together the story of how these giants formed, how they lived their fiery youths, and how they came to be the quiescent behemoths we observe today. What seems like a simple, tranquil galaxy is in fact a time capsule, a living fossil from an era when the universe was younger and more violent. Astronomers have learned to read this quiet light. By studying the colours and motions of the stars, they can piece together the story of how these giants formed, how they lived their fiery youths, and how they came to be the quiescent behemoths we observe today. Each observation peels back a layer of mystery, revealing hints of the galaxy's dramatic past hidden beneath its calm exterior. What seems like a simple, tranquil galaxy is in fact a time capsule, a living fossil from an era when the universe was younger and more violent. Even in their repose, many of the largest ellipticals reign at the centers of clusters of galaxies, surrounded by dozens or even hundreds of smaller neighbor galaxies. Around them stretches a vast, invisible atmosphere of superheated gas filling the cluster, an envelope reaching far beyond the galaxy's stars. This gaseous halo shines faintly in X-rays, a testament to its extreme heat. Astronomers once expected that over time this hot gas would cool and sink into the giant galaxy, perhaps sparking a new round of starbirth to rejuvenate the aging giant. But in case after case, those cooling flows never arrived. The gas remained stubbornly hot, hanging in space like a perpetual heated fog that refuses to condense into new stars, leaving the elliptical's decline unbroken. In theory, the enormous halo of gas around a giant elliptical galaxy should be a cradle for new stars. As this hot gas radiates its energy into space, it ought to cool over time. Astronomers once pictured it settling and condensing, like warm vapor in the air cooling into droplets of rain. They expected a slow, cooling flow of gas sinking toward the galaxy's center, growing denser and colder, eventually igniting bursts of star formation in the aged galaxy. It was a compelling idea. Perhaps these dormant giants could get a second wind, fueled by a gentle rain of cooling gas, lighting new stars in their cores. But when they looked for signs of this cosmic rainfall, astronomers found a perplexing drought. The giant ellipticals were not sprouting new star clusters or young blue stars as expected. Instead, these galaxies remained much the same, old stars shining, with hardly any fresh generation to join them. The vast quantities of gas were indeed cooling in theory, radiating away energy, yet the final result, cold clouds collapsing into stars, was largely absent. It was as if the cooling had been stymied, halted before starbirth could begin. A mystery hung over these galaxies. Why was the star-making rain failing to fall? Clues began to emerge from detailed observations of the hot gas itself. Orbiting telescopes that could see in X-ray light revealed more about this mysterious halo. Instead of a smoothly cooling atmosphere, the X-ray images showed disturbances, vast bubbles and cavities in the gas, some spanning tens of thousands of light years. There were ripples and shock fronts visible, as if some powerful events had stirred this cosmic cauldron. The gas was cooling, yes, but it was also being continually agitated and heated by an unseen force. Something was preventing it from settling down into the calm, cool reservoir needed for new stars to form. All evidence pointed toward the heart of the galaxy, the central supermassive black hole, as the culprit behind this interference. Though these black holes often lie quiet in the present day, they are capable of tremendous outbursts when they feed on infalling material. Astronomers realized that each time the black hole woke from its slumber and gorged on gas, it unleashed a surge of energy into the surrounding halo. Like a cosmic furnace turning on, it heated the gas and pushed it outward. What should have been a gentle, cooling drizzle was being transformed into a hot wind, driven by the galaxy's own central engine. In those X-ray images, scientists could actually see the footprints of these violent outbursts. The vast bubbles in the hot gas were essentially cavities blown by jets of particles and energy shooting out from the vicinity of the black hole. When the black hole had a feeding frenzy in the past, it fired off two oppositely directed jets at near light speed. As those jets ploughed into the surrounding gas, they carved out great holes, like two giant cavities in the intracluster medium. These cavities, filled with energetic plasma, rose buoyantly through the hot gas and dispersed their energy into it. The effect was like dropping stones into a pond. Waves of pressure and sound rippled through the gas, stirring and reheating it. The end result was clear. The gas never had a chance to cool quietly. Whenever it started to lose temperature and sink, another outburst from the black hole would erupt to reheat it, maintaining a delicate balance like a cosmic thermostat. One striking example comes from the Perseus cluster, where the central elliptical galaxy has giant cavities in its surrounding gas. X-ray observations show two vast, bubble-shaped voids about 50,000 light-years across, one on each side of the galaxy's center. These align perfectly with radio lobes observed in the same region. Clear evidence that powerful jets from the galaxy's central black hole carved out the bubbles. The surrounding hot gas is pushed aside and heated in the process, exactly as astronomers suspected. Instead of cooling into a cascade of new stars, the gas was reheated by the black hole's outburst. This dramatic scene in Perseus gave scientists vivid confirmation of how a black hole's radio voice prevents new stars from forming. Through this feedback loop, the galaxy effectively regulates its own atmosphere. The central black hole acts like a caretaker that refuses to let the gas cool enough to rain down. As a consequence, The hoped-for revival of star formation in giant ellipticals never materialized. These galaxies remain red and dormant because each time nature tries to ignite new stars via cooling gas, the galaxy's core fires back with energy to snuff that process out. The cooling flow that astronomers once imagined has been replaced by a cycling interplay of cooling and heating, a stalemate that keeps the galaxy in a kind of extended middle age, never rejuvenating, but also never completely running out of hot gas to shed. Occasionally, a trickle of gas does manage to slip through this cosmic prevention. In a few ellipticals, observers have detected faint filaments of cooler gas, or a sprinkle of new stars forming at a very modest rate. These are tiny embers compared to the conflagration that was expected from a full cooling flow. They suggest that while the black hole's influence is strong, it's not absolute. A small fraction of the gas finds a way to cool, but overall, the grand rain of star-forming gas that was predicted simply does not occur. The giants remain largely unchanged, with just a few sparse signs of new life amid a vast sea of old stars. The mystery of the cooling flows was solved not by new stars, but by recognizing the quiet power of the galaxy's central engines. The very force that once may have briefly turned some ellipticals into ferocious quasars in their youth now serves as a throttle, keeping new star birth at bay. Today, those central black holes are mostly dormant, but the imprint of their past fury remains. The hot gas still bears the scars of their outbursts, the cavities and ripples that speak to what happened. And beyond the X-rays, in the invisible radio waves, the echoes of those ancient eruptions linger. The galaxy's black hole essentially spoke in bursts of radio energy to say no to cooling flows. It is a silent message now, detectable only with radio telescopes, but it tells the tale of why these giants stay quiet. Those radio-bright relics, the ghostly lobes and long-faded jets, are the whispers of that tale. To human eyes and optical telescopes, an aging elliptical galaxy appears serene and unassuming. But if we tune our instruments to the radio waves, a different picture emerges. Many of these galaxies, so quiet in visible light, are surrounded by immense lobes of faint radio emission. It is as if the galaxy that has fallen silent in one way is still softly speaking in another. These radio lobes are the ghosts of a more tumultuous time, lingering whispers from the galaxy's past. Stretching out on opposite sides of the galaxy's core, the radio lobes form twin reservoirs of energy, tens or even hundreds of thousands of light years across. They balloon far beyond the visible stars, occupying volumes of intergalactic space that dwarf the galaxy itself. In extreme cases, a pair of lobes can extend over 1 million light years from end to end, making the host galaxy seem like a tiny spark at the center of an immense radio cloud. Each lobe is a broad, diffuse cloud of high-energy particles and magnetic fields, glowing at radio frequencies but invisible to normal sight. If we could see them with our eyes, we would behold two enormous, faintly luminous halos billowing out from the galaxy's center, like a pair of cosmic lungs exhaling the relic breath of a long-past eruption. These monumental structures are the direct aftermath of the galaxy's energetic youth. Long ago, when the central black hole was actively feeding, it launched powerful jets that bored through the galaxy's gas and into the space beyond. Those jets inflated bubbles of plasma, the very cavities seen in X-ray, which then expanded outward over millions of years. The radio lobes we observe today are the dissipating remnants of those bubbles. They are filled with electrons spiraling around magnetic field lines, a process that emits radio waves. In essence, the lobes are giant, fading billboards announcing that once a quasar lived here. Over time, these radio structures begin to dim and disperse. The energetic particles that light them gradually lose their vigor, and the lobes start to blend into the cosmic background. What might have been a brilliant radio beacon eons ago is now a faint murmur that only our most sensitive radio telescopes can detect. Eventually, given enough time, the lobes will fade away entirely, their energy spent and their particles diffused into space. In the present epoch, many ellipticals carry such relics already well into this fading phase, nearing the threshold of cosmic silence. A few ellipticals still have active radio jets today, blazing forth like cosmic beacons and creating fresh lobes that shine clearly. But in most cases, the active phase is long over, and only the dim afterglow remains. The once thunderous voice of the galaxy has been reduced to a faint echo. In these giants, one must strain with sensitive instruments to catch those final whispers before they fade into the cosmic background. For instance, the giant elliptical galaxy M87 in the Virgo cluster is one such case. A narrow, bright jet of particles shoots out from its core, visible even in certain optical images as a bluish streak. M87's radio lobes billow far beyond its visible stars, indicating that its central black hole is actively energizing the surroundings even today. It stands as a modern example of an elliptical still speaking loudly in radio, whereas many others have only faint echoes left. The existence of these radio voices was a revelation in the early days of radio astronomy. When scientists first scanned the skies with radio telescopes, they found some galaxies were unexpectedly loud at those wavelengths. Often, those turned out to be giant ellipticals. To optical observers, nothing obvious betrayed the drama. The galaxies looked like placid ellipses of light. Yet the radio telescopes picked up massive twin lobes of emission extending from them, sometimes dwarfing the galaxies in size. It was a striking discovery. These apparently sleepy galaxies had a hidden story of violence that only a different ear, tuned to radio, could hear. The radio lobes eventually fade away entirely, leaving the giant galaxy in true radio silence. But even as the echoes of its past die, the galaxy's evolution continues in other, quieter ways. For an elliptical titan, the remaining changes come not from within, but from without, in the form of small companion galaxies wandering in its gravitational embrace. This subtle dance, the slow merging of satellite galaxies, becomes the final act in the life cycle of these cosmic giants, a gradual consuming of stragglers that stretches across the ages. Far from the bright center of a giant elliptical galaxy, in the dim outer halo, a few small companion galaxies circle like moths around a flame. These are dwarf galaxies, little collections of stars, perhaps 1,000th the mass of the giant, lingering in orbit. They are the survivors, the last remnants of a larger population of satellites that the elliptical likely had in its youth. Over billions of years, many others have already been captured and consumed. What remain now are just a handful of stragglers, bound by gravity and slowly weaving around their enormous host in a silent cosmic dance. Gravity ensures that this dance will not go on forever unchanged. Each small galaxy's orbit gradually decays due to a process known as dynamical friction. As it moves through the extended halo of stars and dark matter, it loses energy, almost as if wading through a cosmic syrup. Slowly, but inexorably, the dwarf's path spirals inward, century after century, millennium after millennium. The distance between the satellite and the giant decreases. There is no sudden plunge or dramatic collision, just an almost unnoticeable tightening of the orbital ballet. Given enough time, the little galaxy will draw close enough that the tidal pull of the giant begins to tear it apart. When that moment comes, the encounter is not a violent crash, but a gentle unraveling. The larger galaxy's gravity stretches the smaller one, pulling stars loose from its grasp. A trickle of stars starts to drift from the dwarf, forming a faint bridge of light between the two bodies. Over time, that trickle becomes a stream, and the dwarf galaxy is drawn out into a long tail or arc of stars swirling around the big elliptical. Eventually, the core of the little galaxy itself dissolves, its remaining stars dispersing into the halo of the giant. What was once a distinct galaxy becomes part of the diffuse outer glow of the elliptical, a minor infusion of fresh stars into an ancient system. Astronomers have actually caught glimpses of these final dances in progress. Deep images of some nearby giant ellipticals reveal ghostly streams and arcs of stars in their halos, the tidal remnants of devoured satellites. In other cases, subtle shell-like patterns ripple around an elliptical's outskirts, concentric loops of starlight that likely formed when past companions were absorbed. These shells and streams are like cosmic fingerprints, evidence of the giant's slow cannibalization of its neighbors. Though they are faint and often require long exposures to detect, they tell a clear tale. The big galaxy has been feasting, bit by bit, on those around it. One well-known shell galaxy, designated NGC 3923, displays more than a dozen concentric stellar shells in its outskirts, like ripples on a pond. Each shell is thought to be the vestige of a small galaxy that merged into the elliptical, leaving behind a trailing pattern of its stars. Such systems provide clear snapshots of past cannibalism. Even in our own cosmic neighborhood, we can see similar phenomena. The Andromeda Galaxy, a spiral destined to become an elliptical in the future, shows faint streams from smaller galaxies it has devoured. These observations reinforce that the slow dance of satellites and their ultimate demise is a common chapter in the life of large galaxies. For the giant elliptical, each merged satellite is a nearly imperceptible change, just a trickle of new stars added to a vast reservoir. The overall structure and appearance of the galaxy remain largely intact. Only sensitive measurements or deep images can hint that something was added. Yet, over immense periods, these minor meals do add up. The massive galaxy grows, even if only by a few %, and its halo becomes enriched with the debris of those it has consumed. This growth is nothing like the furious mergers of its youth. No bursts of star formation or dramatic transformations occur now. It is slow accretion in twilight, a final phase of growth that can continue for many billions of years. If we could watch this process sped up, a time-lapse over billions of years, we would see the giant elliptical quietly picking off its companions one after another. A dwarf galaxy would draw near, become a strand of stars, and vanish into the halo. Then another, and another, until none are left. The big galaxy's outskirts would gradually grow denser with each ingestion, like a faint aura strengthening in brightness. But in real time, over a human lifetime, none of this is perceptible. The dance is too slow for any one generation to witness. Only the cosmos itself keeps track of the steps taken over epochs. In time, the giant elliptical may run out of partners entirely. It will stand virtually alone, having subsumed all the available satellites in its vicinity. In some cases, a galaxy ends up isolated, not because it ate everything around it, but because it formed in an empty region of space to begin with. Not all ellipticals reside in bustling clusters. A rare few drift through the cosmos, with scarcely another galaxy in sight. These are the lonely giants of the cosmic voids, massive ellipticals marooned in darkness, living out their days without a cluster or group to call home. There are places in the universe so empty that a single galaxy shines alone across millions of light years. These are the cosmic voids, vast expanses with scarcely any galaxies at all, like immense black oceans between the brighter continents of galaxy clusters. In one of these voids, you might find a lonely giant elliptical adrift in quiet isolation. No bustling cluster surrounds it. No nearby spirals or companions crowd its skies. It is a majestic island in a nearly uninhabited cosmic sea, living out its existence with only the faintest of galactic company, if any. How does such a solitary titan come to be? Perhaps it was born in isolation, forming from a large, pristine cloud of gas in the early universe that happened to sit in an underpopulated region. With few neighbours around, it grew largely on its own, unperturbed by the kind of frequent mergers that occur in denser areas. Alternatively, it might have started as a small group of galaxies that merged together early on, coalescing into one big elliptical and leaving no other sizable companions. Whatever the history, the result is an unusual sight. A massive galaxy without a crowd, a ruler without a kingdom. In the emptiness of a void, the conditions around the galaxy are profoundly tranquil. There is no giant cloud of heated cluster gas enveloping it, no X-ray halo from a surrounding cluster's atmosphere. The only gas and material nearby are those belonging to the galaxy itself. This means the lonely giant experiences very little external interference. It isn't buffeted by the gravitational tugs of passing galaxies or shocks from cluster gas. The galaxy's outer regions can expand freely into the void, and any tenuous gas it sheds simply drifts away into vast nothingness. This is cosmic solitude at its purest. The galaxy, and practically nothing else, for millions upon millions of light years. One of the most extreme empty regions known is the Boötes void, an expanse hundreds of millions of light years across that contains only a handful of galaxies. If a giant elliptical were situated at its center, it would truly be marooned in space, with practically no companions for tens of millions of light years in any direction. Such an environment is almost hard to imagine from our perspective in a galaxy group. The sheer emptiness around that solitary galaxy would mean an undisturbed life, but also a lack of external stimuli or new material. It's the cosmic equivalent of a lone tree in a vast desert. Imagine standing on a distant planet within that solitary elliptical galaxy, looking up at the night sky. The view would be strikingly different from the sky in a rich galaxy cluster. Around you, the heavens would be filled with the usual stars of your own galaxy. But beyond that, there would be a deep darkness. You might spot a handful of faint smudges, perhaps one or two distant galaxies far away at the edges of the void. But the sky would lack the multitude of galaxy glows that would be present in a more crowded universe. The cosmic night would feel especially vast and empty, a true wilderness of intergalactic space, with your home galaxy as the only beacon of light for tens of millions of light years in every direction. From a scientific perspective, these solitary ellipticals offer a unique opportunity to study a galaxy's life in near isolation. They are like natural experiments. How does a massive galaxy age when left almost entirely to its own devices? Without the constant interactions or infalling material that galaxies in clusters experience, an isolated elliptical's evolution is driven mostly by internal processes. Its stars age and die, its central black hole goes quiet, and any gas lost from stars drifts off undisturbed. In some cases, researchers have noted that void galaxies can retain a bit more gas or exhibit subtle differences in their star populations, perhaps because they evolved more gently. Each lonely giant carries clues about how environment, or the lack of it, shapes a galaxy's fate. Such lonely giants are quite rare. In surveys of the cosmos, astronomers have identified only a few massive ellipticals that dwell in these underpopulated voids. When one is found, it becomes a subject of fascination, a cosmic loner that somehow thrived far from the usual galactic cities. These galaxies remind us that even in the most remote corners of the universe, where conditions are vastly different from crowded clusters, the processes of galaxy formation and aging still forge familiar outcomes. They stand as beacons of structure in a desert of emptiness, quietly shining to themselves. In their solitude, they underscore the diversity of environments galaxies can inhabit, from the busiest hubs to the loneliest wilderness. Yet whether surrounded by neighbors or drifting alone, every elliptical galaxy faces the same ultimate destiny, a slow, steady dimming as the eons pass. Even these lonely giants, untouched by external events, cannot escape the silent work of time. Their most massive stars are long gone, and the remaining stellar populace grows ever older and fainter. Now we turn to how all ellipticals, in company or in solitude, undergo a gentle erosion under time's hand as their light fades and they drift toward cosmic invisibility. As cosmic time stretches on, the changes that await an elliptical galaxy are subtle but relentless. These galaxies, already quiet and aging in the present epoch, will continue to fade over the coming billions of years. With no new stars igniting, each passing million years finds the galaxy just a little dimmer than before. The process is imperceptible on human timescales. From our vantage point, an elliptical may seem eternally unchanging. But across cosmic ages, the difference accumulates. The once bright swarm of stars that made the galaxy shine will gradually lose its luster, star by star, like a city going dark, one lamp at a time, as its inhabitants leave or fall asleep. Over the next several billion years, the remaining medium-mass stars in the elliptical will exhaust their fuel. Many of the orange and red giants that still populate the galaxy will shrink and shed their outer layers, ending as faint white dwarf stars. Each such transition removes a bright star from the galaxy's nightscape, replacing it with a tiny, dim ember. With every passing epoch, the balance of the galaxy's light shifts toward these less luminous remnants. The overall color of the galaxy, already reddish, will grow even redder and fainter as the last luminous giants wink out, leaving behind an ever-increasing population of cooling stellar cores. Fast forward to a time far beyond our current age, tens to hundreds of billions of years ahead. By then, almost all the stars left shining in the elliptical will be the longest-lived ones, the red dwarfs. These small, dim stars can burn their fuel slowly for trillions of years, outlasting all other kinds of stars. The galaxy, once teeming with a variety of stellar colors and sizes, will by that epoch be a much more monochromatic place. Its light will be dominated by the faint, reddish glow of countless red dwarfs. No bright blue stars, no hefty yellow suns, not even red giants will remain. Only these persistent, ember-like stars, quietly fusing hydrogen in their cores with feeble light. Eventually, even those durable red dwarfs will run out of fuel. This is a timeline almost beyond comprehension, trillions upon trillions of years into the future. One by one, the last active stars will flicker out, each red dwarf shrinking into a hot but fading white dwarf. When that happens, the elliptical galaxy will no longer have any true stars in the traditional sense, only stellar remnants. Imagine a galaxy that was once a glittering metropolis of stars, now transformed into a graveyard of faint cinders. White dwarfs, neutron stars, and black holes will be all that remain. The silent corpses of a once vibrant population. For a long span, the white dwarfs will still provide a ghostly glow. These stellar embers can shine for trillions of years as they slowly cool. But given enough time, they too will fade to black. Theoretical calculations suggest that after perhaps 100 trillion years or more, even the white dwarfs will have radiated away most of their heat, turning into cold, dark, black dwarfs that emit virtually no visible light. At that stage, the once grand elliptical galaxy would be practically invisible. It would exist still as a gravitational collection of mass, billions of stellar remnants and dark matter bound together. But to an outside observer, it would appear as a darkened shell with only the faintest whisper of any glow. If some far future traveller or astronomer could behold it in that era, they might not even recognize it as a galaxy at all, without the beacon of starlight to reveal its presence. Meanwhile, the universe itself will have changed dramatically by those far future times. Dark energy is driving galaxies apart, and in tens of billions of years, galaxies outside the local group or cluster of our elliptical will have receded beyond the observable horizon. This means that even before the galaxy's own light fades completely, the rest of the universe will effectively disappear from view. An observer in that distant era, living in or near our elliptical, would see an empty sky with no external galaxies at all. The night would hold only the faint glow of whatever remains in their own galaxy or cluster. The cosmos will have become an ocean of isolated islands, each galaxy or cluster alone in the darkness, unable to see the others because space has expanded so vastly between them. And what of the mighty black hole that once anchored the center of the elliptical galaxy? In a cosmos without fresh fuel, even that leviathan will eventually fall quiet and simply sit, a dark mass among dark remnants. Over an inconceivably long span, googles of years, a one followed by 100 zeros, the black hole too will not last. Through the trickle of Hawking radiation, it will slowly evaporate, losing mass bit by bit, until one day it vanishes in a final whisper of energy. By that time, the universe will be in its old age, and the last identifiable piece of the former galaxy will be gone. All that will remain is a smattering of subatomic particles and photons, thinly spread in expanding darkness. The grand elliptical, once a titan of stars, will have been reduced to nothing but a memory in the fabric of space-time, its substance returned to the void. In this quiet finale, an elliptical galaxy's journey illustrates the ultimate poetry of the cosmos. Even the greatest of cosmic giants live out their lives and gently fade away. There is no cataclysm at the end, only a slow hush falling over a once bright empire of stars. It's a reminder that the universe, for all its grand scale and energy, moves toward tranquility in the end. In the deep silence that follows, one can almost sense a kind of peace, the calm after eons of cosmic history, as the elliptical titan becomes one with the darkness it came from.